Hello viewers, today I am covering number system and codes. This is a very important topic in computer organization and architecture subject because in digital computer we use binary number system, and for its compact representation we use a hexadecimal number system. This number system is little different from the decimal number system what we use in our day-to-day life, and later topic of computer organization and architecture like the floating point number system, error detection and protection code, and memory addressing in assembly programming. They all will be using this binary number system or the hexadecimal number system. So it is very important that we learn this first before we can cover those topics. So let's start from the beginning. So here I am introducing the number system. You know that the decimal numbers are written like that, like this 987.34, and with a subscript 10. It means it is a decimal number system, and the point is called the decimal point. In binary number systems there are only two digits, 0 and 1. So it will be a string of zeros and 1, like here 101.01 with a subscript 2. It means it is a binary number system, and the point here is called the binary point. Now this number in positional notation, you can see all these digits have their position starting from 0 just before the point 0, position 0, 1, 2, 3, like this. And after the radix point, this point is actually called the radix point. After the radix point, the positions are -1, -2, -m, etc. So for decimal number the radix is 10, and for binary number the radix is 2. So uh, not only they are indicated with their position, these digits, they also have some polynomial notation by which we can know what is the value of the digit 9. Okay, so we, as we call 900, so we know that the value of 9 is 9 times 100, right? And the value of this 8 is 8 times 10, and value of 7 is 7 times 1. So all these positions have their positional weight that is given in this polynomial notation. So this is the digit multiplied by the radix. So if it is a decimal number, it is 10 to the power n minus 1. So because this 9 for this decimal number, its position is second, because we are counting from 0, right? First position is 0, then 1, then 2. So it will be 9 times 10 to the power square plus 8 times 10 plus 7 times 1. So this is the integer part. Now the fraction part, they are in according to the polynomial notation. It will be -1 here after the radix point. So it is 3 times 10 to the power -1 plus 4 times 10 to the power -2, like this. So here another example is given with a decimal number 251.41 with a subscript 10. That means its value is 2 times 10 square plus 5 times 10 to the power 1 plus 1 times 10 square plus 4 times 10 to the power -1, because this 4 is after the decimal point, plus 1 times 10 to the power -2. Okay, this is the way to find its value. Similarly, we can find the value of this binary number. So it will be 1 into 2 to the power 2. So this is 4. And here it is 0, no? So the 0 times 2 to the power 1 is 0. And then it is 1 times 1. So the total here in the integer part is 5. And then it is coming 0.1 times 2 to the power minus 2. So it is 5.25 in decimal. So here it is giving another number. You know the binary digits are 0 and 1. So binary numbers are a string of zeros and 1. So here it is a big number 11010.11 with a subscript 2. So if the subscript is given, you know it is a binary number, because otherwise it could be a decimal number also, no? By default, no subscript, we can consider it as a decimal number. But with the subscript 2, it is a binary number. So let's see what is the decimal equivalent. So this one, 1 times 2 to the power 4 plus 1 times 2 to the power 3, like this you compute, and it is coming out to be 26.75 in decimal. Okay, and 2 to the power 10 is 1024 if you compute, and this is called K or kilo in binary number system. 2, 2 to the power 20 is this big number which is called mega in binary number system, and 2 to the power 30 is this big number and it is called giga. So other number systems are also similar. So in octal number system, the base is 8, and there are 8 digits are there starting from 0, 1, 2, 3, 4, 5, 6, 7. So this number, if the subscript is given as 8, you know that this is an octal number. If no subscript is given, by default, it can be a decimal number also. It cannot be a binary number because of 274, but it can be a decimal number. But when the subscript is given, you know that it is an octal number. So what is the decimal equivalent of it? It is 1 times 8 square plus 2 times 8 to the power 1 plus 7 times 8 to the power 0 plus 4 times 8 to the power minus 1, which is only 87.5 in decimal. So hexadecimal number system, there are 16 digits are there. So the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it is A, B, C, D, E, F. Total 16. And the value of F is 15. So from here it is 10, 11, 12, 13, 14, 15. 0 to 15, total 16 digits in hexadecimal number system. Now this number B6 5F with a subscript 16. It is a hexadecimal number, and what is its decimal equivalent? You know B is equivalent to 11. So 11 times 16 to the power 3 plus 6 times 16 square plus 5 times 16 to the power 1 plus 15 times 16 to the power 0. So this is 46687 in decimal. Okay, so viewers, you can also pause the video and have a detailed look of this slide. So let's write the numbers, decimal number system. It's only few numbers are written from 0, 1, 2, 3, 4 up to 16, and its binary representation is also given here. You can see 16 is 10000. So to write a number in binary, we are using 5 digits, whereas in decimal it is 16. So binary representation is not very compact. So that's why to refer something we use the hexadecimal number system, but digital computer understands only zeros and ones, so but they use the binary numbers only. But for our sake, we use the hexadecimal number system or a octal number system for compact representation of a big strings of zeros and ones. So this is the equivalent octal numbers are given, and equivalent hexadecimal number is given here. So let's do binary arithmetic. Binary digits are only 0 and 1. And let's see the addition. If you add 0 plus 0, it is 0. 0 plus 1 is 1. 1 plus 0, 1. 1 plus 1 is 2, right? In decimal. But in binary, it is written as 1, 0. Okay. So that is for single digit addition. Now let's see an example with a big number. First number is called the oggend with what you are adding, and the second number is called the addend. So you know how the addition goes on, just like decimal number addition. We start from the least significant digit and keep going to the left hand side to the most significant digit addition. But every location can have only in the result have only one digit. But if the result is two digit, that most significant digit goes as a carry. We call it carry. So let's see the addition. 1 plus 1 is 2. 2 in binary is 1 0. So out of that 0 we write here, and 1 goes as a carry. Now we are adding this 1 plus 1, again 1 0, 0 here, carry here. So here in this column it is only 1 1. So here it is 1. Here again 1 plus 1, so 0, carry goes here, and then again 1 plus 1, 0, 1, 1 plus 1, 0, 1, nothing is here, so it comes here. So even the oggend has only 6 digits, but the result has 7 digits. So when we are adding numbers, the data word should be enough to keep the extra digit. There shouldn't be any overflow. Otherwise, the result will be wrong. Now let's see the subtraction. We know the borrowing concept from decimal number subtraction. So when subtracting, we keep the big number as minuend and the smaller number as subtrahend. And let's minus 1 minus 1 is 0. Now 0 minus 1 cannot happen because 0 is small than 1. So we have to borrow. If we borrow from here, this digit will become 0 and that 1 will come here, which is equivalent to 2. 2 minus 1 is 1. Now 0 minus 0 is 0. Again 0 minus 1 not possible. And here there is no 1 here, no? So you cannot borrow from here. You have to borrow from here. So with respect to this location, this is 4. So you are borrowing basically 4, that you are distributing 1 here, which is 2 plus 2, 4. And this digit will become 0. So now 2 minus 1 is 1, and 1 minus 1 is 0 and 0. Okay, so this is the result. Let's see the octal arithmetic. Octal digits are 8 digits, 0, 1, 2, 3, 4, 5, 6, 7. So we will be minusing, adding oggend with addend. So 1 plus 4 is 5. 7 plus 5 is 12. So 12 has 12 in octal. 12 in octal is 14, right? So 4 you write here, 1 goes here. Now you are adding this column. 4 plus 1, 5, 12. 12 in decimal is 14 in octal. So 4 goes here, 1 goes here. Then again 5 plus 1 plus 3 is 9. 9 in decimal is equivalent to 1 1 in octal. So 1 goes here, 1 goes here. That 1 comes here. So this is the result, octal result. Now for subtraction, uh, we cannot do minus 3 from 1. We have to take a borrow from here. If you borrow here, this 5 becomes 4, and this 1 0. 1 0 is equivalent to 8, right? 8 plus 1 9, total 9. 9 minus 3 is 6. And now 4 minus 4 is 0. Again, you cannot do 4 minus 6, so you have to take a borrow from here. So this 7 will become 6, and this 1 0 is 8. 8 plus 4 is 12. 12 minus 6 is 6. And then 6 minus 5 is 1. Let's see the hexadecimal arithmetic. Hexadecimal digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we are adding 9 plus 8 is 17. And 17 is the decimal. So that equivalent in hexadecimal is 1, 1. So you keep the 1 here and 1 goes here. Now A is equivalent to 10. 10 plus 1, 11. 11 plus 5 is 16. So 16 in hexadecimal is 1, 0, 0 here. So B is 11 plus 1 is 12. 12 is equivalent to C. So you write C here, and B plus D. D is equivalent to 13 plus 5 is 18. 18 is equivalent to 1, 2. So 2 here, 1 here. This is the sum. Let's see the subtraction. 9 minus 8, not possible. You have to take a borrow. Take 1 from here. So if you minus 1 from B, it will become A. And this 1 0 is equivalent to 16. 16 plus 9 is 25. 25 minus 13. It is 12. And 12 is equivalent to C. Okay, now you are minusing. A minus 0 is A. And then again you cannot do 5 minus 8, so you have to take a borrow. If you borrow from A, it will become 9, and this is equivalent to 16. 16 plus 5 is 21. 21 minus 8, how much? It is a B, 13, and here 9 minus 5 is 4. Okay, so let me solve some other binary number additions. I will be solving it so you can get more clear picture. Let's consider two binary integers. Number 1 is 10111. I want to find out what is its decimal equivalent. So we know their positions: 0th position, 0, 1, 2, 3, 4. So their weights are given 2 to the power 0, 1, 2 to the power 1 is 2, 2 square is 4, 2 to the power 3, 8, 2 to the power 4 is 16. So this number is 16 plus 4, 20, 20 plus 2, 22, 22 plus 1 is 23. And let's consider the second number. It is 011110. So here it is 8 plus 4, 12, 12 plus 2, 14. So this number is 14. Okay. Now let's do the binary addition. So these are the number. Number 1 is 11001, and number 2 is 01110. Okay, so let's do the addition, and then we can quickly verify with their equivalent decimal numbers and their addition. So this is 1. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0, and there is one carry here, 1. So this is 1 plus 1 is 0, and this one goes here. Okay, so let's see their decimal. So the first number is 16 plus 8 is 24. 24 plus 1 is 25. And the second number is 8 plus 4 is 12. 12 plus 2 is 14. Now let's see this number. This is 32 plus 7 is 39. And you can also verify that the addition of 25 plus 14 is 13. Let's see another addition. 1 plus 0 is 1. 1 plus 1 is 0 and 1 carry here. Again 1 plus 1 is 0 and carry goes here. 1. 1 plus 1 is 0 and carry goes here. Now it is 1 plus 1 plus 1 is 1. 1 and here 1. We will verify after getting their equivalent decimal. So this number is 16 plus 3 is 19, and the second number is 16 plus 8, 24, 24 plus 4, 28, and 2, 30. And the result, as we have computed, this is 32 plus 16 is 48 plus 1 is 49. Now verify with their decimal addition. So this is correct. Now let's see binary number subtraction. So here the first number is 110010 and the second number is 1110. So for subtracting, you can only subtract from a bigger number. So the first number should be bigger, that's okay. Now 0 minus 0 is 0. 1 minus 1 is 0. Now here 0 minus 1 not possible, we have to borrow. So from here we cannot borrow, we can borrow from here. So with respect to this position, this is 4. So if we borrow from here, it becomes 0. And then this 4 we can adjust to here and 1 0 here. Okay. So 102 minus 1 is 1. Then here 1 minus 1 is 0. And for this we have to okay, so 1 minus 0 is 1 here. Now this 1 became 0. 0 minus 0 is 0 and here it is 1. Okay, so let's see the decimal equivalent, then we can verify that our subtraction is right. So the first number is 32 plus 16, 48. 48 plus 2 is 50. And the second number is 8 plus 4, 12. 12 plus 2, 14. Now let's see the result. This is 32 plus 4 is 36. So we know that 50 minus 14 is 36. So our computation is right. Next time I will be covering hexadecimal number addition and subtraction. See you then. Hello everyone. In this lecture, I am covering the number system and particularly the base conversion between different way of representing numbers. So, a number is represented with its positional notation. For example, a decimal number is represented as 987.34 with a subscript 10. This subscript 10 means it is a decimal number, and there are in this number system there are 10 unique digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And another example is given in a binary number system. The number is 101.01 with a subscript 2. This 2 indicates it is a binary number system which has only two unique digits 0 and 1. And the point is the radix point or the base point, and the portion which comes in front of the radix point, it is the integer part of the number, and the digits that comes after the radix point, that is the fractional part of the number. Now we already know r is the radix of the base of the number and n is the number of integer digits to the left of the radix point in the integer part, and m is the number of fractional digits, and a with a subscript n minus 1 is the most significant digit, and a minus m is the least significant digit. Now, after representing the number, we have to know what value it represents. For decimal number, we know the value, but for binary number, how much it is, what value it is, that can be determined by a polynomial notation or series expansion. In this polynomial notation, any number of any base is expanded like this. This is the digit, most significant digit, times r is the base to the power n minus 1, the location or the position of that digit. And you keep on, this is the value of that digit in that particular location. And so if you like that, if you sum up all the digits, that means the value of that digit in that location, you get the value of that number. Like 251.41 with a subscript 10 is a decimal number, so it can be expanded like 2 times 10 square, because this 2 is in the second position, plus 5 into 10 to the power 1 plus 1 into 10 to the power 0 plus 4 into 10 to the power minus 1 plus 1 into 10 to the power minus 2. And you get this 251.41. The same thing we can do for the binary number. So what value it represents? So it will be 1 times 2 square, that is 4, plus 1 times 2 to the power 0, that is 1. So integer part is 5, and in the fraction part it is 1 times 2 to the power minus 2. That means 1 divided by 4, which is 0.25. So this number 101.01 with a subscript 2 represents 5.25 in decimal. So this way of representing the number in polynomial notation and evaluating its value, transfer the number from that base to its value in decimal notation, decimal representation. So binary, octal, decimal and hexadecimal, these are the popular number system. In binary number system, it is also called base 2. It has two unique digits 0 and 1. In octal number system or base 8 has 8 unique digits 0, 1, 2, 3, 4, 5, 6, 7. Decimal number system or base 10 has 10 unique digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And hexadecimal number system or base 16 has 16 unique digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after that it uses letters A, B, C, D, E, and F. And A has a value of 10, B has a value of 11, C 12, D 13, E 14, and F 15. So from 0 to 15 total 16 unique digits that can be used in hexadecimal number system. Now, because there are so many number system, there needs to be a conversion method from one number system to another number system. Now, we have seen this polynomial representation of a number. For any number of any base, it is represented in this polynomial series, the digit and the base, what it is using, and the digits position. And now, if this equation is evaluated, it gives us a decimal number. So that is the equivalent of that number in decimal system. Now we need to convert a number of any base A to any other base B, not necessarily a decimal number. So we can first convert the base A to decimal representation and then from decimal representation to base B. And let's see how it is done. So base 1, we have seen it before, how a number is evaluated in a decimal number system, and then we will see the step 2 from decimal to the other number system. Now here it is giving an example of a binary number 1101 0.1, and it is coming out to be 26.5 in decimal after the polynomial expansion. And this number 6 to 7 in octal is coming out to be 407 in decimal, and 6b in hexadecimal is coming out to be 107 in decimal. Now after decimal, suppose we want to convert a binary binary to hexa. So intermediate step was to convert the number in decimal first. So from decimal, how to convert the number in binary, we are going to see. So let's see. Now decimal numbers have two parts. One is the integer part, another is the fraction part. So it can be a decimal real number, integer, then the radix point, decimal point, then the fraction part. Now the rule is different for converting the integer part from the fraction part. So if we have to convert the decimal integer to binary, then we will divide the decimal number by 2 and take its remainder, and the process is repeated until it produces the quotient of 0. The binary number is obtained by taking the remainder part from each division from bottom to the top. So we must remember that we will be collecting the remainder from bottom to the top, and we are going to divide the number until the quotient becomes 0. And this is called the division method. And for the multiplication, for the fraction part, from decimal fraction to binary fraction, we will be multiply the fractional part of the decimal number by 2. Record the integer and fraction parts of the product separately. Repeat the process until the fraction part becomes 0. Sometimes the fraction part doesn't become 0 for a long time, so we take a approximation. We just do 3-4 steps and then stop it. The binary number is obtained by taking the integer part from each multiplication from top to bottom. Let's see with an example, it will be clear. So there are two methods. One is converting the integer to binary, and another is converting the fraction to binary. And this is just a binary conversion. We can convert it to octal. So if we want to convert the decimal number to octal, so here we will be replacing 2 by 8, and here also we will be replacing 2 by 8. And if we want to convert decimal to hexadecimal, then we will divide the number by 16 repeatedly. And for fraction part, we will multiply the number by 16. Let's see, decimal integer to binary conversion. So 23 is an integer number, and we are looking for binary conversion. So we are dividing 23 by 2. So the quotient is becoming 11 and the remainder 1. Again, you divide by 2, quotient is 5, remainder 1. Again, 5 divided by 2 is quotient 2, remainder 1. Again, then 1 and 0, and here 0 and 1. When the quotient is becoming 0, you are stopping, and now you are collecting the remainder. This becomes the most significant bit, and this becomes the least significant bit. So 2310 is equal to 10111 in binary. As I said, it will be the same thing for decimal to octal and hexadecimal conversion, only instead of 2 we'll be using this particular base 8 and 16. So if we have to convert 315 in decimal to octal, we'll be dividing 315 by 8 repeatedly, and then the number is becoming 473 in octal. Similarly, for hexadecimal conversion, we are dividing the decimal number by 16 repeatedly, and we are getting the result 13B in hexadecimal number. So this is about the integer part. Now for the fraction part, it is the multiplication method. Suppose we have to convert 0.479 in decimal to binary. So we are multiplying 0.479 by 2. We are getting the result 0.9580. Now 0.9580 is getting multiplied by 2, and it is giving 1.9160. Then 0.9160 multiplied by 2, the result is 1.8320. And 0.8320 multiplied by 2, 1.6640. And when we are going to report the fraction, this is my most significant digit, and here it is the least significant. So we are reporting it from top to bottom, only the whole part. Okay, so the number is becoming 0111, and we could keep on going, no? Fraction has not become 0, but it takes a long time for the fraction to be 0 for some numbers. So after few steps, we stop it, and the result is this approximate number. Similarly, for decimal fraction to octal conversion, we will repeatedly multiply the fraction part of the decimal with 8s here, and we will be reporting it as 3651 in octal. Similarly, for hexadecimal number 0.47910, we are only taking the fraction part and multiplying it by 16. Every time we are multiplying the fraction with 16, and we are reporting the result from top to bottom 7A 9F. Okay, now I'll be solving some problems by hand also, and let's do that. We have to convert a decimal number to a binary number. The example first number is 100, which is an integer in decimal. So we'll be repeatedly divide this number by 2. We'll be using division method. Now divide 50. So ultimately we got the quotient 0. So now we have to report from bottom to top. So the number will be, so that is the result. 100 in decimal is equivalent to 1100100. You can also verify it with its positional notation, polynomial expansion. So this value, this one is 2 to the power 6 is 64. 64 plus 32 is 96. 96 plus 4 is 100. Let's do another example. Here it is 127 integer, decimal number and integer. So let's divide it. We are dividing 127 by 2 repeatedly in example 2. Okay, so ultimately the quotient is 0. So the result is, let's verify this number with its positional value. 64 plus 32 is 96. 96 plus 16 is 112. 112 plus 8 is 120. 120 plus 7 is 127. So this is right. Now we'll be converting decimal fraction to binary fraction by the multiplication method. First example is 0.57 in decimal. So we'll be multiplying it by 2 and the result is 1.14. Next time we will be multiplying only the fraction 0.14 by 2 and we are getting 0.28. Now 0.28 multiplied by 2 is 0.56. Now 0.56 multiplied by 2 is 1 point. So we can keep going because the fraction part is not 0, but we can stop here and we'll report the approximate representation. That will be, and this time we'll be reporting only the whole part from top to bottom. Okay, so let's verify it. The position after the binary point is 2 to the power minus 1. So this one is 0.5. We got 0.5 from here. So this one gives 0.25. We don't need that. This one gives 0.125. That is also not needed. Next is 0.0625. Because we have gone for approximation. Uh, so this is, we are reporting up to this. Let's solve the second example. 0.12 in decimal, how much is in binary? So 0.12 multiplied by 2 is 0.24. Next time will be multiplying 0.24 by 2 and we are getting 0.48. Next time 0.48, we are getting 0.96. Then we'll be multiplying 0.96 by 2, and here we'll be getting 0.96 multiplied by 2 is 1.92. So we'll be stopping here and report the approximate representation, and that will be 0.0001. And you can verify it because this position in binary is 0.5, this position is 0.25, this position 0.125, and this position is 0.0625, and so there will be more ones after this, but we are reporting up to this. So hope this is clear to you how to convert the decimal integer part and the fraction part separately, and then you can add them together, represent them together. So next time I will be covering decimal to hexadecimal conversion and also binary to hexadecimal conversion direct way, binary to octal conversion in direct way. Hello everybody. In this video, you are going to learn how to convert binary numbers to octal and hexadecimal numbers directly. You are also going to see how the hexadecimal numbers are added and subtracted. This is my third lecture on the number system. In the previous videos, I have introduced how to do the conversion from one number system to another number system. There, I have shown how binary number system, octal number system, and hexadecimal number system are first converted to decimal number system and from decimal number system to other number system. But in this lecture, you are going to see direct conversion from binary number system to octal or hexadecimal without going through the intermediate step of decimal conversion before. If you haven't seen those videos, you will find the link at the end of this video. I will show the display the playlist of the entire playlist of this lecture series on computer organization and architecture. There the number system is also there. As a review, let's see that how a number is represented. A number is represented as a positional notation, n equal to a n minus 1, a n minus 2, dot dot a1, a0, then point a minus 1, a minus 2, dot dot a minus m. Just like this example, this is a decimal number 987.34 with a subscript 10 and 900 because this is in the second position. So it is 9 into 10 square. Here it is 8 into 10 to the power 1, 7 into 10 to the power 0. And after the decimal point, it is 3 into 10 to the power minus 1. And here it is 4 into 10 to the power minus 2. So this binary number 101.01, we can find out its value with the polynomial notation like this. This is the polynomial series expansion and it will evaluate to be 5.25. If we display its digit with its position and then radix r is 2 and then 2 square plus 2 to the power 1 plus 2 to the power 0 like this, it will evaluate to be 5.25. Now these are the popular number system. Binary number system has two digits 0 and 1. So a binary number is just a string of zeros and ones. Octal number, which is also called base 8, it has 8 unique digits and those range from 0 to 7. Decimal numbers from 0 to 9. And hexadecimal number has base 16 and these are from 0 to 9. Then it uses letters A, B, C, D, E, F. And A stands for 10, B stands for 11, C stands for 12. Like this, F stands for 15. Now here it is showing just a small table of decimal number 0 to 16 and its binary equivalent, octal equivalent and hexadecimal equivalent. Suppose this number, decimal number 8, in binary it is 10000. So that means decimal is more compact than binary number. And octal equivalent for 8 is 10 and hexadecimal is still 8. Similarly, 16 in decimal, in binary it is 10000 and octal 20 and hexadecimal 10. So in a computer, the binary number system is used, but because it is not a compact representation, we usually use the hexadecimal number system to represent the same binary number. So we must know how to convert between binary and hexadecimal. So a number has a integer part and a fraction part as shown here, and we know their positional notation and how to evaluate them. I am showing them here again just for a quick reference. For octal number 127.4 octal number, which evaluates to be 87.5, and this is the way to convert the octal number to decimal number and then hexadecimal number. Now we are going to see in this video how to convert the binary numbers to octal directly without going through the intermediate step of decimal number conversion. Because binary base is 2 and octal base is 8. 8 is 2 to the power 3. So any binary number, integer binary number, we are grouping 3 bits together. And this is integer, right? It is to the left hand side of the binary point. So we start grouping from the right hand side. 0 0 0 one group, then 0 1 0 second group, 1 1 1 third group, 0 1 0 fourth group, and then there is only one more digit left, but we need 3, so we can imply, it is implied that there are 2 zeros in front of it. So these 3 zeros together make one octal 0, and 0 1 0, it is only 2 in octal. 1 1 1 is octal 7, 1 0 0 is octal 4, and this is octal 1. So the answer for this big binary number is equivalent to 147208 in octal system. Similarly, here I am showing a real number with a binary point, and you also see the grouping again. Before the binary point, we start grouping from right hand side, 1 1 0, then 1 1 1, and after the binary point we start grouping from left hand side. You can see in the left hand side, from the left hand side after the binary point there is only one digit, but we will assume that there are 2 zeros after it. So 0 0 1 together, it is equivalent to 4 in octal. And then this 1 1 0 is 3, 1 1 1 7, 0 0 1 is 4, 1 1 0 is 3. So the conversion of this real binary number is 3473.4 in octal. For binary to hexadecimal conversion, binary has base 2, hexadecimal base 16. 16 means 2 to the power 4. That's why the grouping will be of 4 bits together. 4 bits, it's a integer number. So 0 0 0 0, then 1 0 1 1, then 1 0 0 1, and then there is only 1 1 left. But we can assume that there are 3 zeros in front of it. If we assume that, it is not changed the value of the entire number. So the hexadecimal equivalent of this 4 0 is 0, and this 1 0 1 1 is B, and 1 0 0 1 is 9, and this is 1. So this number is equivalent to 19D016, and you can see it is so much compact, so it is easy for writing and remembering the number. Now let's see an example of a real number with the integer part and the fraction part, and you can see that after the binary point there are only 2 bits, 1 1, so we have to assume there are 2 more zeros here, and if we add 2 zeros, this number is equivalent to C in hexadecimal, 0 0 1 1 C for 12, and this one 1 0 1 1, it is D, 1 0 0 1 is 9, and 1 1 0 0 is 3. So this is the hexadecimal number 39D point C. Now we are going to see hexadecimal number addition. So this is the first number, which is called augend. It is 5BA9 and D058 is addend, and we have to add them. So we'll do like this. 9 plus 8 is 17, right? Then, so this is decimal 17, and then we are going to convert it into hexadecimal. So 17 in hexadecimal is 1, 1. So the least significant one will go here, and the most significant one will go here as a carry. Okay, so again, I am repeating again. 9 plus 8, we know we'll do the decimal addition because we are more used to think in terms of decimal number, and then we are going to convert it into hexadecimal. 9 plus 8 is 17, and 17 is equivalent to 1, 1 in hexadecimal. So 1 comes here and 1 goes here. Now A is 10, 10 plus 1, 11, 11 plus 5 is 16. And 16 in hexadecimal is 1, 0. Then B plus 1 is C. And 5 plus D, D is 13. And 5, 13 plus 5, 18. 18 is equivalent to 1, 2 in hexadecimal. So 2 goes there, 1 goes there, and this one comes down here. So this is the sum 1, 2, C0, 1 with subscript 16. So it is an hexadecimal number. Similarly, let's do a real hexadecimal number addition. FBA6.AB is the augend and D058.67 is the addend. So B is 11. 11 plus 7 is 18. 18 in hexadecimal is 1, 2. 2 here, 1 here. Then 10 plus 1, 11. 11 plus 6 is 17. 17 in hexadecimal is 1, 1. Then 6 plus 1, 7. 7 plus 8 is 15. 15 is equivalent to F in hexadecimal. Then 10 plus 5, 15, again F. Then B, and then this one is F plus D. 15 plus 13. So it is 28. 28 minus 16. The 28 representation in hexadecimal is 1C. So we write it like this. So this is the answer. Now subtraction, we have to be more careful. I am also given a decimal reference how we do the decimal subtraction. So we'll be following the same procedure except that it is a hexadecimal number. So you know that when we subtract, we can only subtract from a bigger number. So minuend is bigger, larger than the subtrahend, and we use the borrowing system. So 9 minus D is not possible. So we have to borrow from here. So if we borrow with respect to this column value is 16. So we are basically borrowing 16 from here. So 1, 0 here is equivalent to 16 in hexadecimal. And as we have borrowed from here, this B becoming A. So now it is 16 plus 9, 25, 25 minus 13. So this is a C. Okay. Now A minus 0 is A. Now again we cannot do 5 minus 8. So we have to borrow from the next higher position. So we are borrowing 16 here. So 16 plus 5 is 21. 21 minus 8 is a hexadecimal D. Because we borrowed, A became 9. So 9 minus 5 is 4. So this is 4DAC. Now let's see a real number subtraction. The minuend is B483.03 and the subtrahend is 5801.67. Now because we cannot minus 3 minus 7, we have to borrow from the next higher column, but here it is a 0, so we cannot borrow from here. We will be borrowing from here. So with respect to this column is 16 times 16. Okay, so that 16 times 16 we are keeping one 16 here, and another we are keeping 15 times 16 here and one 16 here, and this 3 is becoming 2. Okay, if there is any confusion, you can refer to decimal subtraction. Like here also, these are all decimal numbers. 3 minus 7 is not possible, and you have to borrow, but here it is a 0, so you are from here, if you borrow, basically you are borrowing 100, and this 100 you are distributing here. Here you are keeping 10 and 90 you are giving it here. The 9 here is equivalent to 90 with respect to this. So 10 plus 3, 13. 13 minus 7 is 6 here, and then 9 minus 6 is 3, and then you borrowed from here, it became 2. So 2 minus 3 is not possible, you have to borrow from here. So this is becoming 7 and you are giving a 10 here. So 10 and 2 is 12 here now. 12 minus 3 is 9, 7 minus 2 is 5, 4 minus 1 is 3. So because we are used to decimal subtraction, I just kept that decimal number subtraction here for a quick reference, because when you borrowed from a higher location, how this 0 became 9. But here it is a hexadecimal system. I am borrowing from here, this 3 is becoming 2, and here it is F. And here this 10 is 16. So 16 plus 3 is 19, 19 minus 7 is a C. Then F is equivalent to 15. 15 minus 6 is a 9. Then 2 minus 1 is a 1. 8 minus 0 is a 8. Now 4 minus 8 is not possible. You have to borrow from here. If you borrow, B will become A. And here it is 16. This 10 is equivalent to 16. 16 plus 4 is 20. 20 minus 8 is 12. 12 is a C in hexadecimal. And here it is 10 minus 5 is a 5. So this is the way hexadecimal subtraction goes. Hope you learned it. If you need more time, please pause the video and look again. Hello everyone. In this lecture, you are going to learn how to represent positive and negative numbers, that is called signed number representation, and then radix complement number system and radix complement arithmetic. I have started this video lecture series, and on number system itself I have previous 4 videos, and there I have told you that there are so many different number systems are there: binary, octal, decimal, hexadecimal, and I have also shown you how to do arithmetic like addition and subtraction with those numbers. But that time I only considered the positive numbers. But you know that we also have to consider the negative numbers. So today I'm going to show you how to represent the negative numbers for the computer. Usually when we write on a paper by hand, we usually use this plus and minus sign for positive and negative numbers. So here it is showing n is a number which can be positive or negative, any one of them, and the rest of the is given in positional notation, which you have shown before, and the digits in front of the point, which is called the radix point, is the integer part of the number, and the digits after the radix point is called the fractional part of the number, which you have learned before, and you have also learned how to convert one base to another base. So now we're going to see the signed number representation. So for that, the sign bit is shown here specifically. There needs to be one extra sign bit, and usually this bit is 0 for positive number and s equal to radix minus 1. So if we are considering binary number system, radix is 2. So 2 minus 1 is 1. So s will be 1 for a negative number, and rest of the magnitude part remains the same. But if we are considering a decimal number, so in a decimal number, the base of the number, so for that, the positive numbers is s is 0, but for negative numbers, as the radix is 10, it will be 10 minus 1, 9. So minus 15 representation in decimal number with sign and magnitude will be 9, 15. And here it is written as a subscript 10. 10 is the decimal number representation, and S and M stands for sign magnitude number representation system. So this is one way of representing the negative numbers by use of an extra digit. For binary, it is 0 for positive and 1 for negative. And decimal number system, it will be 0 for positive and 9 for negative number. And this is what is called signed magnitude number representation system. But there are other methods are there. So here we are going to see that other method which is used for a computer and which is called complementary number system. Must have heard of two's complement. So we are going to see that two's complement number, or in general radix complement. Two's complement number system is used for binary numbers, and this radix means in general for decimal it will be tens complement. For hexadecimal we will call it as 16's complement number to represent both positive number. So this is the complementary number system you are learning here. So in general you can call it as a radix complement or R's complement. R stands for the radix or the base of the system, and it is represented, a complement of the number is represented within the square bracket. R is the radix, equal R to the power n minus its number in that number system, and where n is the number of digit in n in the number. Okay, so depending on how many digits we are using to represent the number, that width of the number n, it can represent only few positive numbers and few negative numbers. So here it is saying if n is the number of digit you are using to represent the number, you can represent at the most r to the power n minus 1 minus 1 for as a positive numbers. I will give an example. If you are using 4 bits to represent a number in a binary number system, then you can represent 2 to the power 3 minus 1, that means 7. So 0 to 7 positive number you can represent with bits, and for negative number you can represent up to 2 to the power 3, 8. That means minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. So you can represent one more negative numbers than positive number with n bits of representation. Okay. So for number system, you can use a 2's complement number system. And in 2's complement number system with n bits, you can represent r 2 to the power n minus 1 positive number, and 2 to the power n minus 1 negative numbers. There is, you also heard that 1's complement number. So this is called the diminished radix complement, or r minus 1's complement. So if r is 2 or binary number, so 1's complement will be r to the power n minus the number minus 1. That will be the complement of a number. So let's see it with some numbers itself. So complement number. So this is a binary number which is given. Can you tell me what is this number? How to know its decimal equivalent? So this is 0, 1, 2, 3, 1 in this location has the value of 2 to the power 5 is 32. 32 plus here it is 9, right? And so 32 plus 9 is, this number is 41. So the complement of this number is given with inside the square bracket of 2 is, because here how many digits are there? 1, 2, 3, 4, 5, 6 digits are there. So the complement of the number is 2 to the power 6 minus the number. And what is 2 is 64. 64 minus 41. 23. Let's see. 0, 1, 2, 3, 4. Here it is 16. 16 plus 7. 23. So the complement of 41 is 23 in 6 bits of representation. You always have to mention how many bits of representation you are considering. Okay. So depending on that, these values will be changing. So it is always true that the number added with its complement, here digits, right? 6 digits, 6 or 6 bits here, 6 bits. Here you are getting a result which is 7 bits. But if you just ignore this, the rest of the 6 bits is all zeros. So basically what you are getting is the number added with its complement is all 0 with n bits of representation. So that's why this complement number representation can be considered as the negative of the number. Whatever the number was there, the negative of that number is this. That's why when you are adding the number with its complement, you are getting the result as 0. And here it is showing if you take the complement of the complement, you will get the original number back. Okay. So that's why this 2's complement number system is used in a computer, because it represents the negative of the number. Now here it is showing 2's complement of this number you know this number is 10, positive 10 for n equal to 6. So what will be the complement of the number? Complement of the number will be 2 to the power 6 minus this is this one. Okay, it's a big number. What is this number? You tell me, write me in the comment section. Okay, now tens complement number, because the subscript is 10, the number is 10 in a decimal number system. Suppose this is a number in decimal number system. What is its complement? So we are using 5 digit to represent the number. So the complement will be calculating the power, uh, here it is 10 to the power 5. That's why 5 zeros are there, minus the number. So this is the complement. 27,908 is the complement of 72,092. Can you tell me what is the complement of decimal number 3? Easy. 3 is a 1 digit we are using, so it will be 10 to the power 1 minus 3 is 7. Okay. What is the complement of 30? It will be 70, because 30 has 2 digits. So we'll be using 10 minus 30 is 70. It is like that. So radix complement number system, we may want to find the complement of the number given a number. In the previous slide, we saw that you take 2 to the power minus the number, but there is another way to complement of the number, and that is given here. First, replace each digit ak of the number by r minus 1 minus ak, and then add 1 to the resultant. So if it is a binary number system, you will be minusing each from 1, because it will be 2, 2 minus 1 is 1. You will be minusing each bit from 1, and at the end you will be adding a 1. So this is basically 1's complement plus 1. For binary numbers r equal to 2, complement each digit and add 1 to the result. So here it is showing that this big number, and so you are complementing each digit. You do it from left hand side or right hand side, doesn't matter, because you are considering each bit separately. So you are complementing them, and later on you are adding 1. So this is becoming the complement number. Find tens complement of this number. This is a 5-digit representation. Here also, we are not going to do the minus technique, take 5 minus the number. We are just going to complement each digit. So here we will be complementing 10 minus 1 from, so 9, from 9 will be 9 minus 0 is 9, 9 minus 6 is 3, 9 minus 9 is 0, 9 minus 0 is 9, 9 minus 4 is 5. So 59039, and then you are adding 1. So this is the complement of this decimal number. Hope you are understanding this concept, and if you need more time, please pause the video and look again. So 2's complement number, positive numbers, the positional notation of the number, right? And you know that how many positive numbers you can represent depends on the width of the data. That means how many bits you are using. And for positive number, the most significant bit of the number is always 0. So 0 to n minus 2, right? That means n minus 1. You can have this bit is always 0. 0 to n minus 1 is the total width of the number, and out of that this most significant bit is always 0, and rest of the bits will be representing the positive number, and the number you can represent as I said before will range from 0 to 2 to the power n minus 1 minus 1. And for negative number, this bit minus 1 will always 1, and this is the rest of the digit, and it can represent minus 1 to 2 to the power minus 1. So negative 1 number, the maximum value or the minimum value is 1 more than the maximum positive value. Example of 2's complement number system. So n is this number, you have to represent with 8 bits. In the original number there are 7 bits, right? So you will be considering it is a 0, you add a 0 to make it 8 bits, and this, then if the most significant bit is 0, it is a positive number, and now you want to get the complement of that number, so it will be a number, and so you can see that you already know how to take the complement. You complement each bit, right? Each bit of the number, each bit, this 1 becomes 0, 1 1 0 0 1 0, and then 1, so it will be turn out to be this number. And here you can see that the most significant bit is becoming 1. Took the complement of a positive number and it became a negative number. Now if you add the positive number with the negative number, you will get a 0. So what is the 2's complement number, 2's complement representation of the decimal number 18, negative 18. So you know positive 18 is this in 2's complement. You are converting decimal to binary first for 18, and then you are complement the answer. You can solve it yourself to verify it. Now, what is the decimal representation of this number? If it is a 2's complement number, the initial one is telling that this is a negative number right then. Okay. Other things you do not know yet, but this one, this is a negative number. So it will be a negative decimal number. So to know the number, you take the complement of this negative number. You get this number, minus 24. So complement of the complement, you are going back to the original number. Now we are going to see radix complement arithmetic and why it is good. So in a digital computer, all addition, subtraction with a digital logic hardware. But radix complement number system, you can do the subtraction also with the same adder hardware. So it is saying radix complement number system are used to convert subtraction to addition, which is the hardware requirement. Only adders are needed. Like you have to do a minus b, So you can write it A plus minus B, and this minus B is the complement. If you take the complement of B, you get a minus B, and here it is still adding a positive number with a negative number. And you are using a adder hardware this time, and that's why in a computer 2's complement number system is used to do all addition and subtraction same way. And the range of the number it can represent depends on n number of bits. So the number you can represent ranges from minus 2 to the power n minus 1 to plus 2 to the power n minus 1. So 2 to the power n minus 1 is this number, right? Some positive number it can represent is the most significant bit 0, and all other bits are 1. And for this number, negative number, the most significant bit is 1 and all others are 0. That is the range of numbers. It can be represented with n bits of 2's complement number system. So when you are doing arithmetic, you have to pay attention whether the result falls within this range that the number system can represent. If the result of an operation falls outside the range, we call it as an overflow. It is called overflow condition is said to occur and the result is not valid. That means if you consider still n bits of result, it's a wrong result. So the remedy is to increase the data width. So we'll be considering these three cases to see when the overflow is occurring or for overflow detection. Let's consider we have two numbers B and C, and all these cases we'll be considering both B and C are positive numbers. Now first case is when adding two positive numbers. Here in the first case overflow may occur, and in case we are subtracting a number from another number. In this case, the overflow will not happen because the result will become smaller. In this case, when you are adding two negative numbers, then also overflow may occur. So first case and third case, overflow will occur. Second case, overflow will not occur. And we are considering both B and C to be positive initially. So case 1, we are doing A equal to B plus C. So if A, the result is greater than 2 to the power n minus 1 is overflow. Because we know that maximum positive number can be represented is 2 to the power n minus 1 minus 1. So the result cannot be more than that. So here you are using example is 7 plus 4 in decimal it is written, and you have to add them, and it is said that use 5 bits of complement number system representation, 5 bits. So here these numbers are very small, so overflow shouldn't occur, right? 7, 10 is equivalent to this binary. And in 5 bits of representation, this 0 you are adding for a positive number, and 4 is represented like this, and 5 bits representation you are adding this extra 0, and when you are adding them you are getting this result. Okay, and this is positive 1011, so 11. This is number 11, and here no overflow. Basically, when you are adding to positive number, this most significant bit which tells you right away whether it is a positive and negative number will tell you that overflow has occurred or not. You added to positive number and you are getting a result as positive, so no overflow has occurred. So 5 bits of representation is okay for in this case. But in this example, 9 plus 8 in decimal it is given. So 9's representation in binary number, binary and 2's complement number system is a positive number. 8 is also positive. When you are adding them, you are getting this result. 5 bits of representation, right? And in the most significant bit, you are getting a 1, which tells you that it is a negative number. But that is not possible because you are adding two positive number. How can it number? So in this case, overflow has occurred and this is a wrong result. That means you have to increase the, instead of 5 bits representation, you have to use 6 bits of representation. Now case 2 is A equal to B minus C. I know that overflow cannot occur. So here we'll be considering both B and C to be positive. And because we have to minus it, we'll be taking the composite to make it a negative number. And then we are going to do simple addition. Okay, so here overflow will not occur. So no overflow in this case. So here it is giving an example 14 minus 9 in decimal. So you represent them with binary and then you, because it is a 5 bits of representation, you are adding this 0 in front and it is a positive number also. And 9 and you have taken the complement of it, no? So that minus 9 became this number and you are adding them now and you got this result within the 5 bits and this is a positive. You are subtracting a small number for a big from a big number and you got a positive result. So here the result is okay. No overflow has occurred. Now, if you subtract a big number from a small number, like this in this example, you are subtracting 14 from 9, then also it is okay. You subtract it this because it belongs to case 2, so it is okay. No overflow has occurred here. Now case 3 is A equal to B minus C, and in also overflow can occur. If it is outside the range of the number, it can represent. You know that the maximum negative number, it is from minus 1 minus 2 to the power 8. It has that range. And in this case, a overflow can occur if the sign bit is 0, right? You are two negative numbers you are adding, the result should be negative. But if you get them as 0, then you know that overflow has occurred. So like this, minus 7 minus 8, using 5 bits of 2's complement, you do it. And here you are getting the result. The sign bit is still negative, so no overflow. But in the second case, when you are doing minus 12, which will be minus 17, right? In minus 17, you cannot represent in 5 bits. So when you are doing it, you can see the result is this 0. The sign bit position has a 0. So you know that a overflow has occurred in this case. Please pause the video and you yourself know how to represent decimal to binary and how to take complement to complement, and you do the math and check for the sign bit values. Now see another example. 25, A is 25, B is minus 46, and using 8 bits of 2's complement. 8 bits is a big number to represent these small numbers. Overflow will occur here also. A 25, 10 is, this is the 2's complement representation, and minus A will be this, and B is this is the representation. So you do all of them, A plus B, you are getting minus A minus B, you are getting plus 71. There won't be any problem because you have taken a big data with 8 bits of representation. And B minus A also no problem. Minus A minus B plus 21, no problem. So you can summarize the whole thing, how to detect overflow has occurred or not. So let's assume B and C are positive number. So first case, if the sign bit is 0 and carry we are not, means whatever outside the range of digit, that is the carry. So sign bit is 0, two positive number you are adding, you got a sign bit 0. Overflow occurred? No. But if the showing that it has result is negative, overflow occurred. And B minus C, no overflow, it is not possible. Minus B minus C overflow can occur. Two negative numbers, the sign bit 1, but if it is 0, then overflow has occurred. Okay, this is given in a tabular way how to detect overflow. Now we see when numbers are represented using 2's complement number system, addition add to, subtraction add 2's complement of the subtrahend to the minuend, and carry bit is discarded and overflow is detected as above. Radix complement arithmetic can be used for any radix. Here I have shown both binary radix and decimal radix complement, and it can be any radix point, octal, hexadecimal, or any other numbers. Hello everyone. In this lecture video, I am going to tell you how to represent floating point numbers, or what is floating point numbers. This number representation follows a standard given by Institute of Electrical and Electronics Engineering, and the name of the standard is IEEE 754 for single precision number representation, and the same for double precision number representation. I have started this number representation, base conversion, sign and magnitude, and 2's complement number representation in my previous video. So if you haven't gone through them, please go through them. And today particularly I will show you what is floating point number representation. We needed the required foundation to come to this point. So if you haven't got the number representation foundation before, please go through those videos also. Now, in a computer system, various codes are used. The codes are like systematic use of a given set of symbols to represent some information. Like from a daily life example, I can talk about the traffic light signaling system, where red light is used to stop the traffic, yellow light for caution, and green light for go. So similarly, the number representation system follows the codes or a systematic use of information. So far we have seen fixed point number representation, where a number will have the integer part, then the radix point, then the fraction part. And as the number is represented with a number of bits or the data word, so how many bits will be before the radix point will be fixed there, and how many bits will be used to represent the fraction is fixed there. And in that number representation system, there is some drawback or limitation. In fixed point numbers, you can only represent a finite range of numbers, which is less than what floating point number can represent. So floating point number will represent a bigger range of number, and the precision of any measurement we can express in more detail or more precisely in floating point number representation. So as a foundation for fixed number representation, previously I have gone through that those numbers are represented as a sign and magnitude number, or as a 2's complement number or 1's complement number, and where the integer will be represented with a sign bit. uh, 1 is for negative number, 0 is for positive number, and then the magnitude part in binary or in hexadecimal anyways. And then for integer, the radix point is implied, it is at the end to the right hand side. And we usually don't use that radix point because it is the integer and there is no fraction part. And for fraction, we use the sign bit and then the implied radix point. We usually write 0 point and then the magnitude of the fraction. That's the way we represent a fixed point number. Now we are going to see what is floating point number and how it can be represented following that IEEE 754 standard. So for representing floating point number, like n is the number, n is m times r to the power e, where m is the mantissa or the magnitude, r is the base of the numbering system, either binary or decimal or hexadecimal, any base you are using, and capital E is the exponent part. So same number we can represent like this, m divided by r, because we are dividing by 1 r, we will be adding that here, r to the power e plus 1. Or we can represent it like this, m times r multiplied by r to the power e minus 1. So as a practical example, if m is my number, a binary base number 1101.0101. So this number I am representing by moving the binary point in front of all digit, and because I am moving it towards the left 4 bits, I am multiplying it by 2 to the power 4. Because you know each location, each position has a weight of 2. Here it is 2 to the power 0, 2 to the power 1, 2 squared, 2 cube. Because the binary point is moved to the front, it became a fraction, so you have to multiply it by 2 to the power 4. Same number you can represent it like this, 0, 1, 1, adding 1 extra 0, so here the exponent is also increasing by 1. Or you can add 2 zeros in front of the number, and here you are writing it as 2 to the power 6. So if you are writing in so many different ways, that means the data word required uh, for this representation, the third one, is more. Or if the data word is still the same, then you are losing the least significant bits. You have to ignore them because you cannot accommodate all the bits in that particular limited data width. So, for floating point number, a standard method is used that is called normalization of the number, and it is assumed that normalization is used for a unique representation. Mantissa has a non-zero value in its most significant digit position. So this is not a normal representation. This is not, but this one is a normalized representation because it is point. If I consider it is most significant digit, then this is a normal representation. So before going into the how to represent the exponent of the floating point number, we also have to see some other coding method, and that is called excess or biased representation. You must be all knowing the 2's complement number representation. I have also gone through the 2's complement number in my previous video on number system. So there you have seen that if the bit pattern is 0000, in 2's complement number system it is 0, and this particular number 0100 is equivalent to 4, and 1000, when it is starting with a leading 1, these numbers are all negative numbers, like 1000 is -8, and the last one 1110 is -2, like this. So all four ones 1111 will be -1. So that was the 2's complement representation. Now, if we want to use excess 8 code, then with every number, 2's complement number, if you add 8, 8 is equivalent to 1000 in binary. So you will get a excess 8 representation. So if you add with 0, 1000, you are getting this, right? So it is equivalent to -8. So in excess 8 representation, all zeros -8, because -8 plus 8, you will get all zeros. So this is -8, and 0100 is -4, and it is like this. So here you learned a new thing, what is excess or bias representation, and it is actually applied on a 2's complement number, and that excess can be anything, excess 16 or excess 128, etc. Now, floating point number, n is the number m times r to the power e, where m is the mantissa, or called the significant, is a significant, and it has significant digits of m. And e is the exponent, is an integer exponent. This exponent is integer. And we can write the number n like this, right? Positional notation. It can be a positive or negative number, and then this is the radix point. From here, a0, a1, it goes up to a n minus 1 subscript, and in the fraction part it goes from a minus 1 to up to a minus m. So in this representation, total n plus m bits are used, okay, to represent this real number. This much is used. Now, for a floating point number representation, we can move this point, this radix point in the front. So now you are getting this an minus 1, then it will, then at the last it is a minus m. All n plus m bits are here after the radix point, and then you are saying it is multiplied by r to the power n. Because you moved the binary point or the radix point in bits, you have to multiply it. The exponent will become n, r to the power n. So m is usually represented in sign and magnitude, the m part. This is the m part, and this is the exponent part. So M will have a sign and magnitude. Sign bit 0 for positive, 1 for negative, then point, and then this is the mantissa, and it is called radix and sign and magnitude representation of the mantissa. So this thing represents the magnitude and SM represents the sign bit. Okay. Now the exponent will be some excess k representation. So E is usually coded in excess k 2's complement. K is also called a bias. And what is the K? K is usually how many bits for K? So K is selected to be 2 to the power E minus 1, where E is the number of bits to represent the exponent. Okay, you are getting it? So if it is 8 bits for keeping the exponent part, so it will be 2 to the power 7, right? So 128 will be added with the exponent. So this E will range, then E will range from minus 2 to E minus 1, minus 2 to the power E minus 1 to 2 E minus 1 minus 1. So this you have seen, no, in 2's complement number, what is the range of number it can be represented. Suppose there are 4 bits I am using to represent a number in 2's complement number system, then the it will range from 0 to minus 8, right? 0 to minus 8 will be the range. Or it will range from 7. 7 is the maximum positive number you can represent, and minus 8 will be the minimum number that can be represented. So similarly here also it is the same. So excess k form of E is written like this. It is the bias E minus 1 bit, then bias E minus 2 bit, like this. It will range from 0 to E minus 1, means you are using E number of bits to represent the exponent. So combining all the part together, the sign and magnitude part, then the actual mantissa, then after the sign and magnitude, you actually keep the exponent part, and then at the last, you keep the mantissa part. So this is the full representation of the floating point number. So sign bit, then this many E number of exponent bit, and then N plus M mantissa bit. So this number will be minus 1 to the power Sm. If it is negative, minus 1 to the power 1 is a negative. If it is a positive number, it will become plus here. Minus 1 to the power 0 is plus 1. And then this was the mantissa in the fraction part of the mantissa. And then this is the exponent r to the power. This is the bias. This is the exponent with bias, and now you are minusing the bias part because you added 2 to the power e minus 1 as a bias. Okay, so this will be the actual number that you have represented as a floating point number representation here. So if I give you an example, it will be clear. And before that, again, it is shown pictorially how where the bits are kept. First, the sign bits of the mantissa is kept. Then these bits are for the exponent E, and then the last bits are for the mantissa M. This is the floating point number format. Now let's see if this is a number, real number given in binary base system, how it will be represented as a floating point number. And here it is saying that for mantissa you have n plus m, total 10 bits, and for exponent you have 5 bits. So 10 plus 5 plus for sign, you can have the data with this 16 bits of data. So you tell me how to represent it as a floating point number. So first of all, you will be moving the binary point at the front. So it is becoming like this. Now see, in the fraction part, there are only 9 bits, but representation is for 10 bits. So you will just add 1 0 at, at the last. It's not going to change the value of the fraction, but you are utilizing all 10 bits. Okay. So this is the number as two binary number as sign and magnitude. This is the number. And now exponent was 2 to the power 6. 6 is the exponent. Okay. So 6 is given as a decimal number. First you convert it in a binary. 0 1 1 0 in binary is equivalent to 6. But to represent the exponent you have 5 bits, so you are adding another 0 in front. So it is 0 0 1 1 0. So it is binary number uh, um, and a binary number to 2's complement number system. Okay, so exponent is a 2's complement number system, and mantissa is just a sign and magnitude binary system. Remember, these are different. This is sign and magnitude for mantissa, and because it is plus 6, no, this is in 2's complement number system. It is like this. And now suppose you are adding, here it is said that to represent the number, add excess 16 to the 2's complement. So this was the number 6 plus you are adding 16. 16 is 10000. So it is becoming 10110. So this is the exponent in excess 16. So combining everything, here is the sign bit, then 5 bits of exponent and 10 bits of mantissa. So this will be the floating point number representation. This is not the IEEE standard. In our computer nowadays, we are using 32 bits number system. In old computer now we are using 64 bits. So IEEE 754 standard was given in 1985 as a 32-bit single precision number system, and then in 2008 they changed also, they incorporated also the double precision 64-bit number system. And this standard was developed in response to divergence of representation. All computer vendors should use the same number representation system so that they can process the data with the same amount of precision. And that's why this corporation IEEE, they devised this standard for the number representation, the real number representation. So now see, we know that there are two formats. One is for single precision and another is for double precision. For single precision, total data width is 32 bits, and for double precision, total data width is 64 bits. Out of that, first bit is signed for both, and then exponent part for single precision is 8 bits, and the fraction part for single precision is 23 bits. So 23 plus 8 is 31 plus is 1 bit, total 32 bits. And the actual number that can be represented in this format is minus 1 to the power s. S can be 0 or 1 depending on the sign of the mantissa. And then here you see in the fraction 23 bits, but there is a hidden 1 is also there, which is not represented in 23 bits. So you are getting one more bit here. So 1 plus fraction and then times 2 to the power exponent minus bias. Okay, so we are going to see how to represent the number, then we'll get the experience. And so if 1 plus fraction with this 23 bits of fraction, so it will be, the mantissa will be 1.111123 maximum, I'm saying. So it will be very close to 2. Okay, and if the fraction part is all 0, it is still 1. So mantissa will range from 1 to 2, equal to 1 and very close to 2, because instead of 23 bits, if you have 52 bits, then it will be more close to 2. Okay, so so this number representation always has a leading pre-binary point 1 bit, so no need to represent it explicitly, it is a hidden bit, and significant is fraction with the 1 point something. An exponent excess representation, actual exponent plus bias, and for single precision bias is 127, and for double precision bias is 1023. In your previous slide you have seen usually the bias is 2 to the power e minus 1, e is the number of bits for representing the exponent, but here actually they are taking one less. Instead of 128 they are using 127, and for double precision they are using 1023 as bias. So this is the single precision number system with 32 bits, and this is the double precision number system with 64 bits. Sign bit part is the same. Here 8 bits of exponent, here 11 bits of exponent, here bias is 127, and the exponent can range from minus 126 to plus 127. And for double precision, the exponent ranges from minus 1022 to 1023. And here 23 bits of fraction, here 52 bits of fraction. And this double precision was came much later in 2008 when computers started using 64 bits of data width. Okay, some features about this number representation system. Single precision 32-bit, double precision 64-bit, and the significant bits is 23 in the fraction part, plus 1 hidden, which is the before the fraction. And then significant ranges from 1 to very close to 2. This number is very close to 2. And exponent bit is 8, exponent bias is 127, and if you want to represent a 0, then exponent will be all 0 and fraction will be all 0. And the normal representation, like exponent all 0, fraction not 0, this is not a normal representation. And for infinity plus minus, exponent will be 255, fraction will be 0, and for nan not a number, exponent 255 if not 0. And ordinary numbers, the exponent will be from 1 to 254, which is minus 126 to 127. And the minimum number that can be represented is 1.2 in decimal into 10 to the power minus 38, and maximum number that can be represented is 3.4 into 10 to the power 38. So that is a big range of number that can be represented with 32 bits of data word. And similarly for double precision, you can go through it. So this exponent all zeros and all ones are reserved, that is not ordinarily used. So for smallest value, 7 zeros and 1, an actual exponent is minus 127, which is told in the previous table, previous slide, and fraction is this 1.0. So this is the minimum number and this is the largest value of the number, which you have seen in the previous slide. And similarly for double precision, okay, so why is the exponent is biased? So there must be a reason, no? It is not 2's complement number. It is again biased with excess 127. Why? For faster comparison, for sorting, etc., and allow integer comparison of floating point numbers. So when you are going to see, you have to do arithmetic where the numbers are in floating point. There you have to compare, no, in multiplication or for addition, you have to compare. So this comparison become easier with this excess number representation system. So here an example is shown. If you want to represent half means 0.5 in unbiased exponent, then it will look like this. Half means 0.5, right? And 0.5 in binary is 0.1, but your uh, binary point should be 1. There should be a leading 1, so it is 1.0 to the power 2 to the power minus 1, and these all ones, 8 ones, is equivalent to minus 1. And so this is the exponent part, and 1.0, all zeros in the fraction part in the unbiased system. And with biased system, if you add minus 1 plus 127, so it will become 126. This will be the representation. Similarly for 2. 2 means 2 to the power 1. So it is 1 0. In binary it is 1 0, right? So you have to shift the binary point. You have to make it 1.0 and then 2 to the power 1. So exponent is 1 and fraction is all 0. So if you are adding the bias, 1 plus 127 is 128 here, and the fraction part. So decimal to IEEE 754, how to convert them? The basic techniques are given here. Represent the decimal in the form of plus minus 1.xxx and then 2 to the power y, and fill in the fields. Remember biased exponent and implicit 1 mantissa. So with that, these numbers you can convert. You can convert all the solution is already given, but I will be solving one problem with you. And so the conversion can be both ways, decimal to IEEE 754, and if the number is given in 750 IEEE 754, how to convert it in decimal. The answer is given here, okay? But I will be solving one of them with you. Suppose you have a number minus 0.75. It is a decimal number. How do you represent it as a single precision number? IEEE 754 single precision number. So first decimal to binary. This is the binary conversion. Minus 0.11. This 0.1 is 0.5 in decimal, and this one is 0.25. So this is from decimal to binary. Now you have to normalize the number. So that means you have to push the shift the binary point towards right, and this is a negative. So this is minus 1 to the power 1. Then this becomes 1.1 and 2 to the power minus 1. Okay. Now you have to add the exponent. This is the exponent. Minus 1 plus 127 is 126. 126 in binary is this. And for double precision, you are adding 1023 as bias. So it is said this is the sign bit, then this is the exponent part, and this is the fraction part. Okay. Now the other way of conversion, if a number is given in IEEE 754 standard, what is the value in decimal? So we can see that the sign bit is 1. We can see the green color bits are for the exponent, and it is coming out to be 129. And now because this is bias was added here, now you will be minusing the bias part. So 129 minus 127 will be only 2, and this is the fraction part, so there will be 1 implied, so it is 1.01. So this is the number minus 1 into 1.01 is 1.25 in decimal, and this is 2 square, which is minus 5. So hope you understood it, and if required, please pause the video and go through them again. And there are several examples were given in the previous slide. Please solve them yourself and write me in the comment section if you have any problem. Hello viewers, welcome back. Say hi to my pet Dino. He's so eager to meet you all. So in this lecture video, I'm going to tell you how to do floating point arithmetic. Floating point numbers are represented with IEEE 754 standard. I have introduced this topic, how to represent floating point numbers, in my previous video. So if you haven't seen that video, please go through it first. It will give you the required foundation, and I'm giving the link for that video here. So just a quick recap here also. The floating point numbers n has a mantissa multiplied by radix to the power exponent. It is basically a real number with a mantissa or significant part. But in scientific notation, it is represented like this: mantissa multiplied by radix to the power exponent. And we are going to see uh, in how many different ways we can write this number. Like the same number, m, if I divide by r, then we have to adjust the exponent by adding 1 there. And if I multiply the mantissa by the radix, we have to adjust the exponent part by decrementing it by 1. So here it is giving the example. Here it is my number, the whole mantissa given here, 1101.0101. So this is a real number expressed in binary form. But in scientific notation, we usually write it like this: 1.1010101 multiplied by 2 to the power 3. You can draw the analogy from the decimal number representation, how the scientific numbers are represented to the power 10. So it is similar to that. It is only radix is 2 here. Now the same number can be represented as 0.1101, and here the exponent is increasing because the mantissa decreased, and similarly for the other representation also. Now, because the same number can be represented in so many different ways, we need a standard way of representation, and that is called normalizing the number. In normalizing the number, we keep 1 in the most significant digit. So it is written here that mantissa has a non-zero value in the MSD position, most significant digit position, then it is normalized. So according to that definition, first number is normalized, others are not. Now we have to see how many digits or bits we can keep this number, right? If the fraction part is very big, it will not accommodate in the data word. So IEEE 754 format has specified number of bits allotted for exponent and mantissa. But before that, this is the organization for keeping them here as a number. So the first bit is for the sign bit of the mantissa, and then comes the exponent, and then come the mantissa. Okay, so first sign, then exponent, and then mantissa. And this sign bit is for the mantissa part, not the exponent part. And mantissa is represented as sign and magnitude binary number. Remember, it is sign and magnitude. So sign here and only the magnitude goes here. And exponent is represented as 2's complement excess k number. We have gone through this 2's complement number, excess or biased representation before also. So at the end of this lecture, the whole playlist of the number system will also be given. Please go through that also. So IEEE standard number is 754, and it was devised in 1985. IEEE stands for Institute of Electronics and Electrical Engineers, and they wanted a standard way of writing the numbers so that it is universally accepted, and all computer vendors do the number representation in the same way so that the program can be portable from one computer to another computer without losing any precision of operation in the result part. And this standard has two versions. One is called single precision, which takes 32 bits for data representation or the number representation. And this 1985 started with this single precision number representation. And later in 2008, they also added this double precision number, which uses 64-bit bits for keeping the number. Now, you already know this is the organization of the number. First the sign bit, then exponent, then fraction. For single precision, total 32 bits are there. Out of that, exponent takes 8 bits and fraction takes 23 bits. Now, if you add 23 plus 8 is 31 plus the sign bit, 32 bit. And for double precision number, exponent takes 11 bits and the fraction part takes 52 bits. Total, if you add them all, it will come to be 64 bits. Now the number that it will represent is given x equal to minus 1 to the power s. S is the sign bit of the mantissa. It is either 0 or 1, sign and magnitude representation. Then multiplied by 1 plus fraction. See here, there was no bit here for representing this 1. So this 1 is implied. It has no place here in this 32 bit. So it is getting an extra 1 bit here. So 1 plus fraction is the actual mantissa times 2 to the power exponent minus bias. That means this exponent is biased. And for single precision, this bias is 127. And for double precision, the bias is 1023. And I already told you before why this biased representation. It is for some comparison purpose, for sorting numbers. When you have to compare two numbers, it becomes easy to compare them by this biased representation. Now you can see that the significant or mantissa can range from 1.0 to maximum 2, right? Because 1 then point, if all of them are ones, it will all add them up close to 1. So total significant range is 1 to 2. And exponent is excess representation, actual exponent plus bias is given. So this is the standard way of representing floating point numbers for doing computer arithmetic. Now it is shown pictorially. This is for 32-bit format. It has 32 bits here. And for double precision, it keeps 64 bits. It takes 64 bits. And here exponent is 8 bits, here 11 bits, here bias is 127, here bias is 1023. So with bias 127, the exponent will range from minus 126 to 127. So exponent can be positive and negative both. And mantissa is always positive, whose sign bit is here. The front bit is the sign bit. And this is the arrangement. This is the organization of the floating point numbers. Now, these are, if you want to practice how to represent some decimal numbers to floating point numbers, all these examples are given here with their solution also. And this conversion can be both ways, decimal to IEEE 754 or IEEE 754 to decimal. If you have to convert the other way, so this is the number given in IEEE 754 single precision number. What number it actually represents, the solution is also given. So many examples are given with their solution. I want all of you to practice this, and I am going to show you in more detail how to solve one of the problems from each group. So suppose you have to represent the decimal number -3. How will you represent it in floating point number? So because it is a integer number, right? So in binary it will be -112 sign and magnitude. And this number is not written as a normalized form. For floating point number, we have to represent the minus sign as -1 to the power 1, and the number, this 1 we will write it as 1.1. As we are decreasing the mantissa, we will be increasing the exponent by multiplying it by 2 to the power 1. Okay, so the fraction will be from here 1 and all 22 bits of 0, right? Total fraction is 23 bits. So total 1 and then 22 bits of 0. And exponent was 1. With this 1, you have to add the bias 127. It will become 128. And this is the binary representation of 128. So if you are representing -3 as a single precision number, this will be your exponent. And if you are representing this number as a double precision number, the bias added will be 1023. It will be total 1024. So this is the binary equivalent of 1024. There should be total 11 bits here. So the single precision number is this sign bit, and then the exponent part, and then the fraction part. And as double precision, this is the sign bit, and then 11 bits of exponent, and then 52 bits of mantissa. Okay, now let's do the conversion in another way from floating point number to decimal. Suppose we have this number represented as a single precision floating point number. We have to know what decimal number it represents. So we already know the sign bit is 1, and we know the fraction part is this 011 here, and exponent is this. So this exponent is actually 131, right? From binary to decimal conversion, it is 131. But this is a biased exponent. So here we are actually minusing with 127. So it will be 2 to the power 131 minus 127. So the number is -1 to the power 1. Then 1 was hidden, right? 1 point. This is the fraction part 011, and this is the exponent. So you do the math, and it is coming out to be -22 in decimal. Okay, I hope you have understood this, and I want you all to solve all other examples that are given with solution and verify them. Okay, now let's see the floating point addition and subtraction techniques. There are several steps for doing that, and we will be taking one example. There are two numbers are there, 1.000 times 2 to the power -1. And second number is a negative number, 1.110 times 2 to the power minus 2. So first number is 0.5 for quick solution or for better understanding, and the second number is negative 0.4375. Now you know that in floating point representation, the mantissa is represented as sign and magnitude. So no need to do the magnitude part anything because sign bit will come separately. So the first number um, need will be basically subtracted. Second number will be subtracted from the first number, and the result will be 0.001 into 2 to the power minus 1. So the steps are, first of all, you have to align the binary points. So where is the, here it was first number had 2 to the power minus 1 and second number was 2 to the power minus 2. So this is the smaller number. Second number will be shifted towards right. This fraction will be this, basically this binary point will come in front. So binary point is going in the left hand side. So the second number will be here, and because you made this significant part smaller, you are adjusting the exponent, decreasing the exponent. Now both the numbers have the same exponent. So first step was to align binary points, and then second step, so you are adding a negative number. That means you are doing a subtraction basically. So 1.000 minus 0.111 will come out to be 0.001. And then the exponent remains as before into 2 to the power minus 1. Now in the third step, you have to normalize the result and check for over or underflow. Okay, so this is the result, right? Subtracting these two number, but this is not in a normalized form. In the normalized form, there in the most significant digit there is a 1. That means you will be shifting the binary point to the left, and then you have to adjust the exponent. So it will be more negative because you are increasing the mantissa, you have to decrement the exponent. So in the normalized form, it will become 1.0002 into 2 to the power minus 4. And this one doesn't have any overflow or underflow. This topic I'll be covering later. It also depends on how many bits of data word you are using. Here it is saying 4 digit. Within 4 digit you have to represent. So there is no problem. There was no underflow or overflow. And now in the fourth step, you actually do round and renormalize if necessary. After rounding also, the number may be denormal. So you have to normalize it again. So this is the result, and it comes out to be 0.0625. Okay. Now I will also tell you what is the floating point adder looks like and how all the steps are done one by one. And this floating point adder is very different from integer adder. In integer adder, entire addition happens in one cycle, but for floating point addition, so many steps are there. It takes several cycles. That's why floating point adders are separate. If the same adder will be kept for floating point addition, it will take a lot of time and it will slow down the clock cycle for all other operation. So floating point adders are different, and I will show you how complicated it is. So here it is showing floating point adder hardware, and here the steps are also given as a flowchart. So this is one floating point number, this is the second floating point number. So first of all, their exponents will be compared, and how much, what is the difference between those exponent By that amount, the fraction of the smaller number will be shifted. So this it is coming here. These two exponents are subtracted, and their difference is found, and it is coming to a control unit. And control unit will tell which fraction needs to be shifted, left or right. Okay, no, it has to be shifted right, because you are adjusting the smaller number as per the bigger number. And after that, those fractions will be added. The significance will be added or subtracted as per whether the number is positive or negative, because it is a sign magnitude representation, and the result may be denormalized, so it will be shifted left or right to make it a normal number. And then when you are shifting it, the exponent also needs to be adjusted, either incremented or decremented. And after that, rounding will be done, because you have to accommodate the result within the number of bits that is there. And after the rounding, this is also another topic to look into in detail. And if I may prepare another slide for that, video for that. And after that, you will be presenting the number as a floating point number representation as per IEEE 754 standard. So let's see the flowchart, what it says. Start, then compare the exponents of the two numbers. Shift the smaller number to the right until its exponent matches that of the larger number. Then second step is add the significant and normalize the sum with either shifting right or left to normalize it, and then you detect overflow or underflow. If there is overflow or underflow, there should be an exception should be raised that something wrong has gone on in this operation. Otherwise, if everything is right, no overflow, underflow, then this fourth step is rounding. And after rounding also, you need to normalize in some cases if it becomes denormalized, and this will be end of the operation. So now I will be solving few things. Here you see we have to add two numbers, floating point addition. So 7.75 is one number and 0.375 is another number. This is given in decimal. Let's do this math quickly in decimal. So the result will be 8.125. But we are learning floating point, so we'll be representing this number in floating point, and then we'll follow the steps that the adder will do. So 7.75 is equivalent to 1.1111 into 2 to the power 2, and 0.375 is 1.1002 to the power minus 2. Now floating, and I have written it in a normalized form, right? When you are representing this number, you represent it as per IEEE 754 standard. Now what the floating point adder will do? Floating point adder will adjust the exponent of the smaller number. The second number is smaller, so it is doing the shifting of the mantissa part until the exponent becomes same. After the exponent becomes same, it has added them, and you can see after addition it is denormal now, because there should be just 1 point the fraction, but here there are two digits are there. So if you normalize it, it will look like 1.00, and you are adjusting the exponent. And in IEEE 754 standard, the exponent 3 is 3, you have to bias it with 127. So after biasing, 3 plus 127 is 130. So here you see this 8 bits of number represent 130. This is 128 plus 2. So this is the exponent and this is the fraction. See, I have written only this part. I didn't write this one because this one is implied. There is no place for that. So this is the final number representation after doing the addition. In this case, we didn't consider about underflow or overflow or the result becoming approximate, right? So you can see the first number I have used up for in the fraction part, four digits. And here, just by for normalization, now this fraction is 5 bits. So maybe when big numbers with many bits are added or subtracted, there is no place for keeping those extra bits after normalizing the number, least significant bit. And in that case, they are lost. But in this case, we are considering that all the bits are there to be accommodated in the data word. So this example is for subtraction of two numbers. So it is same as the addition steps that I have gone through. Here also to subtract two floating point numbers, the exponent must be equal. If they are not already equal, then they must be made equal by shifting the significand of the number with the smaller exponent. Now in this example, the numbers are 16.75 minus 15.875 and the result is 0.875 in decimal. But we are going to solve in floating point number representation. So the first number 16.75 in scientific notation and in normalized form is this 1.000011 times multiplied by 2 to the power 4. And second number is 15.875. It is 1.111111 times 2 to the power 3. So this is represented in a normalized form. Now we are going to see how the floating point adder will be adding them. So this is the smaller number. Its exponent is made equal to that of the first number. So for doing that, you see this significant part has changed. And now we can align the binary point and we can do the subtraction. But after subtraction, you can see it is a denormal number. So we have to normalize it. So now it is normalized. Now let's represent it as a floating point number, single precision. So this is the exponent, no, minus 1. So we can add 127, then it will become 126. So you can see the green color bits are for the exponent and it represents 126. And the result was positive, so the sign bit is 0 here, and the fraction part is only this part 1100. The leading one is omitted because it is hidden or implied. Okay, so hope it is clear and you solve and practice all the problems that is given here, and see you next time with floating point multiplication and rounding, etc. Hello viewers, welcome to my channel. In this lecture video, I am going to tell you all the steps that are required for multiplying two numbers which are represented in IEEE 754 floating point standard. Please stay till the end so that all the steps are clear to you. Please also like, share and subscribe my channel so that it motivates me to make more lecture videos for you. So let's dive in how to do floating point multiplication. So let's first of all, let's take a simple example where two binary numbers are getting multiplied. And this is called binary point. Digits before the binary point is the integer part and digits after the binary point is the fraction part. And you can notice that first number is called the multiplicand and the second number is called the multiplier. and you have done lots of multiplication in your schools where the numbers were in decimal numbers. Only thing different here is that it is binary, and you already know the binary to decimal conversion. Here it is written, this number here is equivalent to 3.5 in decimal, and the second number is 3.25 in decimal. So if you have a calculator, you can quickly calculate it in your calculator and get the result. And you can later on verify whether the multiplication, where the numbers are in binary, is also giving you the same result. So you take this process of multiplying. This is the multiplicand, this is the multiplier. You start from the least significant bit, and if that bit is 1, you bring the multiplicand here. That means these are the partial products, we call them partial products, and you keep adding the multiplicand only when you are multiplying with a 1. If you are multiplying with a 0, that time you are not adding it. So and every time you are also shifting, you are shifting the partial product towards right, one bit at a time, and the product became this. And if you convert it from binary to decimal, it is 11.375, and if you have computed in decimal, you can verify it is exactly the same. Only here to notice the steps that are to be followed. So floating point numbers also, you will be doing the same thing, only the representation of the number is different here. So here you can see the steps again. In every step, partial product is shifted. Next bit of multiplier is examined. Also a shifting step, because you will be starting from LSB, you will move towards the MSB. And if the bit is 1, shifted multiplicand is added to the product. These are the process. And another thing to notice is that the product takes twice the number of bits as the multiplicand or multiplier. So you have to provide a big register which can hold this product. So the multiplication hardware is like this. You keep a multiplicand in a 32-bit register. In a computer, we are talking about computer. Our computers are either 32 bits or 64 bits. Here we are taking example of multiplicand, which is 32 bit. And we also have a 32-bit ALU, arithmetic logic unit. And here is the product register. So you can see ALU will take two numbers and add them. One is coming from the multiplicand and another is coming from the product. The partial product is coming from there, and those two numbers will be added. But as I told you, only if the multiplier bit is 1, that time it will be added. If it is 0, no addition, only the product will be shifted here. And you can see the product is 64 bits. Initially, in the right hand side, the multiplier is there, and product is only in the leftmost 32 bits. And with every bit of multiplier getting multiplied, it is also shifting there. So the control unit is determining whether to shift or to shift and add both. So these steps are written here. 32-bit ALU and multiplicand is untouched. That means they are not changed or shifted. The sum keeps shifting right, and at every step, number of bits in product plus multiplier is 64. Hence, they have a single 64-bit register. And let's see the flow chart. It is the same which I have told you just now. Start and test the product 0. You test the 0th bit where the multiplier is there. If the product 0th bit is 0, then only shift the partial product to the right. And if the 0th bit of this product register is 1, then you first add the multiplicand with the partial product and then shift. And then you take, is the shift done? All 32 bits here, no? All 32 bits done. Then the multiplication is complete. If 32 bits are not done, the same thing will be repeated. So you can ask me that multiplier need not be 32 bits. So in that case, it will be stuffed with zeros in front of it, and then this process will continue. So now we have to see that the numbers need to be represented in IEEE 754 standard first, and then we have to do the multiplication. So these standards are either single precision, 32-bit, and double precision. And these standards were incorporated so that the programs written and executed by different computers, they all give the same result. For scientific calculation, the precision of the numbers is very important. Precision of the result is very important, and so a universal way of number representation was required, and that's why IEEE incorporated this standard in 1985. And the thing is that in this floating point standard representation of number, the dynamic range of number that can be represented is much more increased than the fixed point number representation. So that's why this floating point standard is taken by the computer's hardware. So this is the IEEE 754 number representation format, in which there are three parts. First one bit, most significant one bit, is for the sign bit, and then next 8 bits for the exponent part. And this exponent is biased. For single precision, it is plus 127, and this 23 bits is fraction. So the actual number that is there in this representation is x equal to minus 1 to the power sign bit into 1 plus fraction. This 1 is not given there, it is hidden, into 2 to the power exponent minus bias. Now the significant is the 1 plus fraction that can be represented will range from 1 to 2. Suppose the fractions are all 0, because there is a hidden 1, so it will be 1. And if the fractions are all 1, then it will be 1.1111. So it is very close to 2, but not exactly 2, because it will need other more bits to make it exact 2. So this is the representation, and you must take a notice that the single precision bias is 127 and double precision bias is 1023. If it is double precision, the whole thing is 64 bits, and here it is 1 bit, 11 bits, and 52 bits. So this is a number representation in floating point standard first. Before we do the multiplication, we represent the number in floating point. So if we have to represent a decimal number minus 5.25, then it will come out to be 101.01 in binary representation. And in scientific representation, it is minus 1 to the power 1 times 1.0101 into 2 square. And for floating point representation, we have to add 127 with 2, so it will become 129. 129 is equivalent to this binary, and the fraction part we will be keeping 0 1 0 0 1 0 1, and all other bits are 0. And for double precision, this is 11 bits, bias is 1023, and the fraction is like this. Let's see the multiplication steps when the numbers are given in scientific notation. First example, which we saw in the beginning, it was just a simple binary number. It was not in any scientific notation. So scientific notation has exponent part. So we must see that first. So these are the two decimal numbers given in scientific notation, and they are 4-digit number. So the first number is 1.110 into 10 to the power 10, and the second number is 9.2 into 10 to the power minus 5. So when we multiply, we add the exponent. You must have known it already, because you have done this kind of multiplication in school. And then we multiply the significant, and later on we attach the exponent part. So right now this number, the result is not normalized or scientific notation, because before decimal point there are two digits. So there should be one. So we are shifting the decimal point and adjusting the exponent. And because the result will also should have 4 digit, we need a rounding. So we are dropping the fifth bit here, and the result given in scientific notation is this. For floating point number multiplication also, we are going to follow the exact same steps, only there the floating point numbers are of fixed, some width is given 32 bits or 64 bits, and there are three parts are given, no, where to keep the sign bit, how long is the exponent, that means how much, how big the number can be or how small the number can be, all are specified there, but the procedure will be the same. First is add the exponent, second is multiply significant, third is normalize the result and check for over and underflow, whether the result can be kept in the specified number of digits or not, and then round and re-normalize if necessary, and then determine the sign of the result from sign of the individual number. If both are positive, then the result is positive. If one of them is negative, then the result is negative. So we all know this, but just to recapitulate. Now we see the same example, multiplication example, but here the numbers are binary and given in scientific notation. So these two are binary numbers. So here also you are adding the exponent, then you are multiplying the significant, then normalize the result and check for over and underflow, then round and then determine the sign. So after all the background, how to multiply, how to represent number as a floating point, we are going to see how to multiply the floating point numbers. Now suppose we will be multiplying two numbers, minus 0.3 times 248.5. This is in decimal, so you can use a calculator and find the answer already, and then later on you will can verify it. So there are several steps in representing the number in floating point. So this is the number one. It has a mantissa into 2 to the power exponent. So this mantissa is actually 1 plus fraction 1, 2 to the power exponent. So 0.3, it has a repeating pattern. 0.01, after that 0011, 0011, and it keeps on going, it never ends. So that's why, because we have to represent the fraction, no, first of all this is the translation of 0.3 to binary, and it was not normalized. No, in case of normalization you have to have a 1 in front of the binary point. So when you normalize the number, you also get the exponent, which is 2 to the power minus 2. And as I said, you only have 23 bits in the fraction part, so you have to round. Now you take the 24th and then you add it with 1. It is called rounding up. There are many rounding techniques are also there. So in this case we are rounding up, so it will become 0 and this 22nd bit will be 1. So this is the translation or conversion of the decimal 0.3 to binary in scientific notation. So this is the fraction part. Exponent is minus 2, and you add the bias, it becomes 125. So this is the exponent. So the whole number is written here. First the sign bit 1, then the exponent, and then the fraction. Similarly for this number 248.5, this is the conversion from decimal to binary, and now after normalizing you are getting 1.1111, this number. So from there you are taking the fraction and you are noticing the exponent 7, and biased exponent will be 7 plus 127 is 134, and in IEEE 754 format it will be 0 because it was a positive number, then the exponent, and then the fraction part. Now we are going to do the multiplication. Here the multiplication is shown exactly the same way. And remember, previously also when we were multiplying the numbers, we just ignored the ignored the binary point, and later on in the product we placed the binary point. In the first example also we have done that. So here this is the first number. Here I have written the hidden one and the fraction. All together it is written. And here also for the second number also hidden one and the fraction. Those will be multiplied. Okay. So if you do the multiplication, I have done the multiplication. These red color ones are all the carries that were produced here. So we have only, first you multiply by 1, you keep the multiplicand here, and then you have to shift, no, that is even here with a cross, and then you see that there are 3 zeros are there. So for that you do not add the multiplicand, so they are also given with a cross mark here. So then when you multiply with this one, then it comes here, then you again shift. Okay, so basically you are adding 6 rows of 6 partial products you are adding, and you are getting this number. So where to put the binary point now? This one has um, it should be 23 bits, right? 23 bits, but there was a 0 here, the LSB, that I have ignored here. So here it is taking the hidden one. There are total 23 bits, and here it is 1 2 3 4 5 6 7 8 9. So 22 plus 8, 30 bits. So from the right hand side, uh, it will have 32 bits, and then you will be putting the binary point here in the product. Okay, so it came out to be this big number. You can see it has many more bits than floating point can represent, so we also have to do some rounding. But first of all, when you put the binary point before 30 bits, you also have 2 other bits in front of it, so it is not normalized representation. So you have to shift the binary point, and it will become 2 to the power 1. So this is a scientific notation, but you also have to do rounding because you only can keep 23 bits in the fraction part. So if you round, you add this one with this. We are always rounding up. You can just ignore also, and there are many other ways of rounding that is also provided by IEEE standard. In some other video I will go through all the rounding technique, but here you note that we are always rounding up. The first number 0.3 also we rounded up, and here this product I am also rounding up. So this one became 0 and this one became 1, and here it became 2 to the power 1 because you had to renormalize the number, and that will be added with the, when you add the two exponent, it will be added. So let's see. So n was this. So you first of all you have to do what will be the sign of the two numbers. It will be first number sign XOR second number sign, and then M1 into M2, mantissa into mantissa, which is the 1.00, everything together, and then 2 to the power E1 plus E2. In IEEE 754 format, because this exponent already has 127 added, 127 is added, so you will minus 127. So it will be minus 2 plus 7 plus 127. I didn't add this 127, 127 and minusing. Basically there is only 127, which is 132, and it is given here, and M1 into M2 was given here, this one. So now your new exponent will be 132 plus 1, because here is 1, you you got a extra 1 as exponent when you normalize the number. So new exponent is 133 and this is this. So the answer of the multiplication in IEEE 754 is this. So if you convert this number in decimal, then you are getting this 74.55, uh, where if you do the decimal multiplication, it is coming out to be 74.55 only. But here you can see, here you have a 3 also, and I didn't compute much more. So this floating point arithmetic, this multiplication is approximate, and it is giving a little bit higher result, because remember, you round it up twice, once when you are representing 0.3, and also in the final product, you round it up in the 23rd bit position. That's why you got a value that is little bit more. So if you use a double precision standard, your result will be much more precise. It will be less than this 3 will not be there, maybe it will be much less. So basically what you have done for multiplication, you are doing XORing the sign of A and sign of B, two numbers A and B, and you are adding A's exponent, number one's exponent, number two's exponent, and you are minusing the bias ones, and then you need a normalizer, and you are multiplying number A mantissa and number B mantissa, and you have to use a normalization again, and this one is giving you the result. So the procedure for multiplication is add the exponent and subtract the bias, and XOR the sign bits and multiply the mantissa. So let's see the hardware for it. This is the two IEEE 754 floating point numbers, sign, exponent, fraction, sign, exponent, fraction. So you are taking the exponent and exponent, you are adding them. In the multiplication, you add the exponents, and then you are subtracting 127 because two numbers have two bias added, so you are subtracting one of them, and then you are multiplying 24 by 24. It is 23 bits in the fraction part, but now this time you have considering the hidden one also, so it became 23 plus 1, 24 bit for both the numbers, and you are creating the product, but you have to round, right, and you have to re-normalize also. So ultimately you will represent as 23 bits, so rounding is needed, and a re-normalization is needed. Whenever you have to re-normalize, you are adding 1 with this exponent that you have already computed, and this is the hardware for floating point multiplier. And the flowchart or the algorithm is also the same. Start at the biased exponent of the two numbers, subtract the bias from the sum, and to get the new biased exponent. Then multiply the significance or mantissa, normalize the product if necessary, shifting to right and incrementing the exponent by 1. And now here another thing you are checking is overflow or underflow. Overflow and underflow occurs only when you are adding two exponents, right? You have only 8 bits to represent your exponent. And when I have gone through the foundation of floating point number representation, I have told you, no, in 8 bits of exponent, you can represent the number ranging from minus 126 to plus 127. If the addition of two exponent is more outside that range or too less, then it is called overflow or underflow, and you are checking it here instead of checking when you added the exponent, because when you are normalizing the number, you are adding 1 with the exponent, no? That time also it may overflow or underflow may happen. That's why this check is given here. And if yes, then it is an exception. The number you are calculating is not right. And if there is no overflow, underflow, then you are rounding again, which the round procedure I have already shown you. And then it is saying, is it normalized? After rounding also it may be not normalized, then you are taking it back here again to normalize. And if it is normalized, then set the sign of the product to positive if the signs of the original numbers are positive. Otherwise it is minus. Okay, so this is the flowchart. So here again I am talking about this exception. What is that exception? As I told you, this exception may happen when there is overflow or underflow in adding the exponent. It is just like any other integer overflow or underflow. So overflow means result is too big to represent in those number of bits, and underflow means result is too small to represent. Both can raise an exception under IEEE 754. For an unsigned number, overflow happens when the last carry cannot be accommodated. And for a signed number, overflow happens when the most significant bit is not the same as every bit to the left. When the sum of the two positive numbers is a negative result, that is not possible, right? So it is a overflow. And when the sum of the two negative numbers is a positive result, and that is also not possible. The sum of positive and negative number will never overflow. So you learned a lot of things. There are a lot of steps there which are needed for multiplying two floating point numbers. Hope everything is clear, and I will come up with another video where the rounding and overflow and underflow is covered in more detail. Hope you like this. If you liked it, please like, share, and subscribe. And thank you for watching my video. Hello viewers, welcome to my channel. In today's lecture video, I'll be talking about computer codes. I'm starting with 4 very simple codes like ASCII code, BCD, run length encoding, and Huffman code. They are very simple but at the same time very much useful in a modern computer. I hope this basic knowledge will generate interest in you to know more about the more complex codes used for image compression, JPEG image, MPEG image, and for cryptography. If you are a college student or a inquisitive learner, this lecture video will be very much useful to you. So please stay till the end of the video, and please don't forget to like, share, and subscribe my channel. So let's dive in. First, we are going to see few definition. What is a code? It is a set of rules that will transform or convert some information in original form into another format. And why it will be converting? Because maybe we'll get some advantage in saving the storage space that will be required, or for transmitting that data in the original format, maybe taking too much of bandwidth. But if you convert it in a coded form, it will save the bandwidth. So that is the definition of a code. It is just transforming the original information into another format. Now, binary code. In the binary code, the code word will have a string of zeros and ones, and that is called binary code. And there are few codes which are fixed length, where the code word will be of same length. Suppose you are converting alphabets, English language alphabet A, B, C, D. So A will also get the same length code, B will also get the same length code. If it is true for all other alphabets, then it will be called fixed length code. Some codes are not fixed length, variable length codes are also there. And we are going to take one example in Huffman coding, and where some alphabet will be represented with a smaller string, some will be represented with a longer string, depending on how frequently they appear. And the code length is the number of bits that is used in a code word. If it is a fixed length code, code length for all the codes are same. And if it is a variable length code, then we take the average code length. So in a binary code, the code word is a string of zeros and ones. And if we use n bits, we can represent at most 2 to the power n distinct information with it. And this n can be any number, but in choosing n, we should keep in mind that the code word should be optimized so that we get the benefit, right? We are transforming the original information into a different format. So we should get the benefit of saving memory space and transmission bandwidth. So code length should be accordingly. And also note one thing, these binary codes, they do not have mathematical representation. They do not mean mathematics, right? They are just a string of zeros and ones. And in most of the cases, it is true. But in one code, we are going to see binary coded decimal. It still has the numeric property. The bits have weight associated and it has a value. So it can be both, but most of the time, this string of bits, they do not represent a mathematics or number, and you cannot do addition, subtraction with them. So the first code in our bucket list is the ASCII code. ASCII stands for American Standard Code for Information Exchange, and it was introduced in 1968. It is also called alphanumeric codes because it transforms alphabets and numbers both. It also transforms all the punctuation marks that are used in English language into some code word, binary code, and it can be the original information can be visible or invisible character, and it will be transformed. Like I have just mentioned some of them: space, null, um, carriage return, line feed, etc. So it was introduced in 1968 to process textual data. The text files, so far we have seen number representation, decimal numbers were converted into binary, but how about the text? And this computer was invented in America. So the first need was converting the English text into some binary string so that they can be processed. And this first code is called ASCII code, and they used 7-bit ASCII code. And with 7-bit, 2 to the power 7, 128 code words could be generated, and that was enough for transforming all the alphabets A, B, C, D, uppercase, lowercase, and the digits 0 to 9, then all the punctuation marks and all the other things like the bell or the carriage return or the line feed, everything was converted with 128 code word. And I'm giving you an example of the ASCII code so that hello can be represented in a computer system. So the code, ASCII code for age with 7 bits was 11010000. They were just assigned. I'm going to show you the lookup table for the ASCII code. So E was this, and hexadecimal, this one is 68, because this upper 3 bits is 1106 and then 1000, this is 8. then E is 65, L is 6C, 6C, and 6F. Okay, and the number 0 also has a ASCII representation, but right now it is not the number 0, it is the character 0, and it is 30 in hex, and 9 is 39 in hex, and all other punctuation marks and invisible characters like space, null, carriage return, line fit, etc. all have some representation in the ASCII code. And another thing is that in a byte, the byte is 8 bits long, right? So ASCII code was 7 bits, and the 8th bit was used as a parity bit. And this parity can be even or odd, anything, but I am giving an example of even parity. So that 7 plus 1 is 8 bits. 8 bits together is called 1 byte. So usually in a computer, the unit of length of data is either a byte or a word, etc. So with 8 bits, you can also add the parity bit, and this parity bit checks if data is transferred from one place to another place, then it is checking that there are 3 ones here, no? And to make it even, their even parity will be 1 here. But for the next letter E, there are already 4 ones are there. Even parity bit will be 0. And like this, it is used. So we can say ASCII code is also 8 bits, where the 8 bit is for the even parity. So let's look at the ASCII codes table. It is called a lookup table. So as I said, with 7 bits, you can generate 2 to the power 7 words, code words. So all of them are listed here from 0 to 127. So total 128 code words are there. So 0, the first code word is assigned to null. And then this 10, decimal 10 or hexadecimal A has been assigned to line fit. Let's see the numbers. This 0, this 48 in decimal, 30 in hexadecimal, assigned to represent the 0 character. And then 57 is assigned to 9, and like that. Capital A is assigned to 41 in hex, then small a is assigned to 97 or hexadecimal 61, and like that all 128 code words are gone that are used in modern computer for English language processing. Now the thing is that there are so many other languages in the world, and nowadays the computer can process all other languages like the Chinese language, Devanagari language, Bengali language. They have their own alphabets. So 7 bits of ASCII code was not enough to represent all of these languages. In the computer also we use emojis and many other symbols are there. They also need representation. So later on the length of the code word was increased, and that is called Unicode, which is universally accepted. And this Unicode has different forms, UTF-8, which is variable length. It takes 1 byte to 4 bytes. Like English language was the first language that was used in ASCII code. So to keep the compatibility in Unicode with 1 byte, this English language will be used. And for other languages like Bengali or Devanagari, more length bytes are needed. So if UTF-8 is used, then it is a variable length code. It will take 1 byte. Maybe it is 1 byte is given to the predominant English language, because English was the first language the computer used. And for Bengali, it will give 4 bytes. So to store something in Bengali, it will take more memory and more bandwidth than that of English. And then in UTF F16 format is also there. Then UTF-32 format is also there. This UTF-32 format is fixed length 4 bytes. In this format, all the languages have the fixed size code word. So English also 4 bytes, other languages also 4 bytes. One disadvantage of this code is that it is just taking too much bytes. So those are the things that need to be taken, like when you measure the efficiency of a code, you see what is more efficient, UTF-8 or UTF-32. Now let's look at the second code, which is called binary coded decimal. In binary coded decimal, individual decimal digits are given a new code, which is a string of binary numbers. So 0 to 9 will have a code, and if it has, I told you before that it has some numerical values also. It is also called 8421 weighted code. And if you have a big number with many decimal digit, then all the digits will be individually converted to code word. And these BCD codes are used for numerical displays. You must have seen it in a hospital where the patients are called and they show that which number of patients are with the doctor right now. Like this, it is used for 7-segment display. And in this also addition and subtraction can be performed, but it is a little different from the other binary number addition and subtraction, and we are going to see that. So this is the BCD code. Here I am showing 0 to 9 decimal numbers, and their codes are 0000, because you know that to represent 9 binary number is 1001, to represent 8 it is 1000. So 4 bits are needed. So it is also an example of a fixed length code. And so BCD code is same as the binary number corresponding to 0 to 9. And but 10, 11, 12, 13, because they are 2 digits with 4 bits, you can have a binary representation, but those are not represented in the BCD code. Not used, not used, not used. So how are they represented? As I am saying that 10 is a decimal number with 2 digits, they will be individually given a binary code. So one example, 1024 is a decimal number. So you just convert them individually, 8421 BCD code. So 1 is 0001, 0 is 4 zeros, and 2 is 0010, and 4 is 01000. Okay, so to represent 1024, you need 16 bits. Let's do another example. 954 is a decimal number, and 9 is represented separately 1001, 5 is represented 0101, and 4 is represented separately as 0100. So the BCD for 954 is 1001, 0101, 0100. This is how you represent decimal numbers having multiple digits. And you can do addition and subtraction also. Let's do one addition with the BCD code. So this is, suppose you have to add 75 with 35, one 7-segment display where the 2 digits can be displayed is showing 75, another is showing 35. If you have to add them, then in decimal addition you get 110, but here you are seeing when you are adding them, you are getting 110, 101. But this one 1010, it doesn't have a BCD representation, right? Because it is the last one was number 9, that was 1001. So 1010 was not used. So you have to correct it So to correct it, you add 6 to both the digits. Remember, because we are not utilizing 6 representation from 16 from 10 to 15, 6 representation we are not utilizing in BCD code. So to skip that, you are adding 6 to both the digits, and then you are getting this code with an extra carry. So right now, after this correction, you are getting the right number. And this is the rule for BCD addition. So what is the rule? Step 1, add the two BCD number using the rules for binary addition. And if a 4-bit sum is equal to or less than 9, it is a valid BCD number. And if a 4-bit sum is greater than 9, or if a carry out of the 4-bit group is generated, it is an invalid result. Add 6, which is 0110, to the 4-bit sum in order to skip the 6 invalid BCD code words and return the code to 8421. If a carry results when 6 is added, simply add the carry to the next 4-bit group. So here there was a carry was also generated. So this is one BCD code, and this the BCD code. Let's look at the BCD to 7 segment decoder, how it works, why it is needed. So BCD 4 bits long BCD codes are there from 00, and the last one is 1001. So when all zeros are coming here to the input to the decoder, here it should display 0. That means these are LED lights, okay, individual LED lights. There are 7 LED lights are there. But when it is all 0 in the input of the decoder, A should be lit, B should be lit, C, D, E, F. Only G shouldn't be lit. Here the input-output function table is given for the decoder. So all zeros, A is 1, A, B, C, D, E, F, all ones, only G not 1. Likewise, where it is 1 in the input side, only B and C should be 1. And it is all others are 0. And it is like that. When it is 9, then A, B, C, D, and after that E is not lit, but F is lit and G is lit. And BCD code is used for 7 segment display. Let's look at the third code, which is called run length encoding, or RLE. It's very simple, very easy code. So it was the first code that was developed, and it is used to compress the data. Suppose you are storing a lot of data, and if you can compress it with less code words, then you are saving memory or communication bandwidth. And suppose there the text is this, there are 17 A's are there, after that 7 B's are there, and 13 C's are there. So total 37 bytes as per ASCII code. I have added the 8th parity bit also to make it full. So the requirement should be 37 bytes. But with run length encoding, you are just counting how many A's are there, and you are writing it 17A and then 7B and 13C, so that you know that this 17 is a count and is not part of the text. You use some special character. I am depicting it with hyphen here. So here you are using total 8 bytes. Originally it was 37, now you are using only 8 bytes. So it is a lot of saving. In example 2, we write like this, excellent, and with so many exclamation mark. So here in RLE it will look like excellent, then 20 exclamation. And a big saving will come when you have an image like this. It's a 256 by 256 image that takes a lot of data to be stored, because these colors are represented with red, green, blue channel pixel values. But if you are doing run length encoding, you will just say that 128 by 128 white pixels are needed and 128 by 128 red pixels. So a lot of savings will come from run length encoding. The last coding algorithm that I am covering in this lecture is the Huffman encoding. It is a variable length encoding. So Huffman coding is a popular compression technique that assigns variable length codes to symbols so that the most frequently occurring symbols have the shortest code. And how you get those code, a binary tree is constructed progressively with the least frequent occurrences to most frequent occurrences of symbols. The branches are assigned 0 and 1 from top to the top of the tree to get the code word. I'm going to show you with example. And Huffman code is also called a prefix code. Here, no code word is a prefix of another code. So when you are converting it back from the code to the original information, there is no problem. I'm going to show you. And if that is the case, we call it a lossless compression technique or lossless encoding. On decoding, the symbols are reassigned their original fixed length code. It is a lossless coding technique, and coding efficiency of Huffman coding depends on the text. It's a dynamic encoding, right? Like the run length encoding and this Huffman, it is dynamic. There is no lookup table, no dictionary where you find, you actually have to process the text and to find out its frequency or how many times it is appearing, and then you are getting the code word. Let's find out the code word with an example. So here my example is America, Africa, India. I have written all in capital letters here. So first of all, ASCII code, we are calculating what will be the, if we use ASCII code, then there are 22 letters are there, counting the commas and the spaces also. And if I use 7 bits ASCII code, it will take 22 into 7, 154 bits there. And we are going to see the advantage of Huffman coding. That's why I have calculated the ASCII code bits first. So in Huffman coding, you take each alphabet A, how many times it appeared. So A appeared 5 times. America has 2 A's. Africa has 2 A's and India has 5. Then next is I. I is 1, 2, and 3 and 4 times. Okay, and I have computed it already and arranged them from highest frequency to lowest frequency. So you can check, verify with some other letter also. R. America has 1 R, Africa has 1 R, so total 2 R's are there. And space, how many space is there? Here one space, another space here. Comma is also 2. Let's see, D is only in India. So after you calculate the frequency of the letters, you create a binary tree. And for creating binary tree, you start with the lowest frequency alphabets, and those will be your leaf nodes. And let's see how it happens. So M has 1 frequency, E has 1. So you combine, you are generating a binary tree. So if you have two children, you can have a parent, right? So M occurred 1 time, E occurred 1 time. So if you combine them to a parent node, so total frequency will be 1 plus 1, 2. You have many such 1 frequency. So you do F and N 1, 1, you are getting another parent 2. Then you are getting another 1 was there. So you are combining it with a 2 and R and D, you are getting frequency 3, total frequency 3. And then you are getting C2 and comma 2, you are getting another frequency. Okay. And then after that, you are combining C and space and this together, and you are getting a total frequency of 4. and here you are combining 2 and 3, you are getting a frequency of 5. 4 and 4, you are getting a frequency of 8. Now you will be combining 5 and 4, and you are getting 9, and here 5 and 8 you are getting 13, and 9 and 13 you are getting 22. So the root of the tree is 22, and these are the leaf nodes. This S is also a leaf node, A is also a leaf node, 4 is also a leaf node. So when the codes will be generated, you will be traveling from top till the to the leaf node. So A will get a code, and it is a binary tree. To one branch you assign 0, to another branch you assign 1, and it is true for all the branches. To one branch you assign 0, another branch you assign 1. So no rules that left has to be 0 or right has to be 1, no such rule. So after doing that, uh, you are traveling from top to the leaf node. So to come to A, you are traveling this 0 and 1. So A should have a code of 0 and 1. And you see this code is very small, only 2 bits, and A occurred 5 times. That's why it was given a small length code, whereas the code for F will be 1000, like that. Okay, you check for others also. So I'm now computing the Huffman code for A 01, Huffman code for I. Where is I? I is here, so it will be 110. It should be 110. Then for R is here, so it will be 1011, and like for all other letters. So now you can see the code words are of variable length. A was most frequently used, so it has got a small code word, and the code words, the letters which are used least frequently, they got big code words. So now my text was America, Africa, India. So it will look like this. And you can see no code word is a prefix to another. And I have actually distinguished each code with a hyphen. They will not be used. Actually, they will not be used. But right now, to learn the code, how it works, I have given those hyphens. Those are extra. And you can see the code for A is 01. And this 01 doesn't appear anywhere in the beginning. So for the 110 code, 110, nowhere 110 is there. So when you are converting this Huffman code to the original text, there won't be any problem. You get 01, and you know 01 is one of the code word, so it is A. And 0010, 00 is 00 is there, 00 is there, but this is not a complete code word, no. So there are 3 options for 00. You check another bit 1. 001 is also not there, uh, and then 0010. When you come to 0010, then you know that it is M. So conversion from this code to the original text is lossless. No information is lost there. Dear learners, today you have learned about some simple but very essential computer codes that are needed for the workings of a computer. First one was ASCII to represent English language. I have also briefly gone through Unicode, which can represent all other languages, but I haven't elaborately discussed that. Maybe some other video I will discuss it. And then the second code was BCD, binary coded decimal, that is used for 7-segment display, run length encoding, and Huffman code. And there are so many other codes are needed, required for a computer system. Next one I will be covering is a error detection and a correction code, or the Hamming code, Hope it is generating interest to you to learn about more codes that are needed in a computer system. If you have liked this lecture video, please like, share and subscribe. Hello learners, welcome to my channel RG Global Academy. In today's lecture, I'm going to talk about few error detection codes. For a computer network, data is transmitted from one computer to another computer, and there is a slight chance that data can be corrupted while transmitting through the noisy channel. Even in the same computer, when the data is stored in memory, there is a slight probability that data may be corrupted. So it is very important that the error is detected at the receiver side and sender protects the data and then only sends it to the receiver. So today I'm going to talk about simple parity check, vertical redundancy check, longitudinal redundancy check, checksum, and cyclic redundancy check codes. These codes vary from their ability to detect errors, and they are listed from weak code to strong code. And we are also going to learn about the few terminology in this field like encoder, decoder, Hamming distance, CRC polynomial, etc. So let's dive in. So data can be corrupted during transmission or in memory. And the solution for that is first detect the error and then correct it. In today's lecture, I'm only going to talk about error detection because correction is more complete. And for correction also we need detection. First of all, let's see types of error. The first one is single bit error. As shown in this figure, 8 bits of data is getting sent, and while transmitting it got corrupted and 1 bit is altered. And that is what is called single bit error. And the chance of single bit error is more than the other kind of error which is called burst error, where multiple bits have changed and those multiple bits need not be consecutive. In this example, it is shown that 4 bits have changed, but their burst length, their span is 8 bits, which is called the burst length. So, single bit error is more probable than the burst error. So, there is a difference between error detection and correction. Error detection is simpler than error correction procedure, and we are doing only error detection in this lecture. So if the receiver detects error, receiver can discard the data and ask the sender to retransmit it. But for detecting error, the sender has to do something. The sender will append few redundant bits to the data word, and the whole thing together, data word and redundant bits together, is called a code word, and that code word will be sent to the receiver. Let's know about another term which is called block coding. In block coding, a group of data bits called the data word is protected by the redundant bits. Suppose the data word length is k bits, then r redundant bits are added. So total k plus r, which is equal to n, will be the length of the code words. So we are going to see today about vertical redundancy check VRC code, longitudinal redundancy check LRC, then checksum, and then cyclic redundancy check. And they are listed in order of their capability. Vertical redundancy check is the basic one, not capable of detecting all kinds of error. Longitudinal check is better, then checksum, and then the cyclic redundancy check. So, to detect and correct errors, sender will send extra or redundant bits along with the data bits. So in the sender side, there is an encoder, and the job of the encoder is to take the data and feed it to a generator which will decide which redundant bits to add and how many bits to add, and then it will be the complete code word. So data and the redundant bits are also called check bits. They are together is the code word, and that is getting sent through noisy transmission line to the receiver. After the receiver receives the code word, it will send it to a checker and check whether the data has been corrupted or not. If not, it will accept the data, and if corrupted, it will discard the data, and it may ask the sender to retransmit the data again. Let's see how the code words are generated in more detail. So if there is a data word which is k bits long, so with k bits there can be 2 to the power k data words, right? And each data word will be of k bits long. Now if r bits are added with that k bits, so the code word's length will be k plus r, which we are calling as n. So there could be 2 to the power n code words, but we need only 2 to the power k code words. So out of 2 to the power n possible code words, 2 to the power k code words are valid and others are invalid. Now the bit that will be added, the simple procedure is parity checking. Suppose we have a 6 bits of data which is shown here 0 1 1 1 0 0, and one extra bit will be added, and by doing a even parity checking, this is it will just count number of ones here, and here in this data there are 3 ones. So in even parity another one will be added, so that in the total code word there are even numbers of ones. There could be a odd parity scheme also. With odd parity scheme, because in the data word 3 ones are there, in a odd parity scheme 1 0 will be added to make even number of odd number of ones. So either even parity or odd parity is applied in a simple scheme. So I'm going to see another example where the data bits 2 bits data word length. So with 2 bits there could be 4 different data words 0 0 0 1 1 0 and 1 1, and one extra bit is added. Here you can see 0 0 and code word is 0 0 0. So it is applying even parity bit, and with 0 1 data code word is 0 1 1 even parity 1 0 1 0 1 1 1 1 1 0. This is the code word. So the data will be added with the redundant bit, code word will be generated, and that will be sent to the receiver. So upon receiving the data, what the receiver will do? Suppose the data sent was 0 1 1. After adding the redundant bit, 0 1 1 was sent. Now receiver knows that 0 1 1 is a valid code word, right? So receiver will accept it. But suppose receiver received 111. How is that possible? Receiver receives 111. Maybe these 0 bits got altered to 1. Then it will be 111. But then receiver will check the valid code words. 111 is not a valid code word. So receiver will discard this code word because the data is corrupted. So other terminology, let's go through them first, and then we are going to see how the number of check bits are determined. So in a data, the weight of the data, suppose I and j be n-bit binary code words, not the data, we are considering the complete code word, then weight of that code word is the number of ones in I. Wi or wj, that will be the weight, and distance of two code word dij is the number of bit position in which I and j are different. And in this coding system, it is important that the code words have more distance. More distance is better than less distance. Suppose here in this example, I is a code word. It is 8 bits long, 011011000. What is the weight of I? I is 4 and weight of J is 3. And you can check in how many bit position they are different. First bit position they are different, third bit position they are different, then this one fifth bit position they are different. So they are distance between these two code word is 3. Now we are going to know about another term which is called Hamming distance, and this is an important term. And Hamming distance means minimum distance between the code word, between the pair of code words. So you are generating 2 to the power k code words, right? So different code words have different amount of distance. So after calculating the distance between all pair of code words, you take the minimum distance, and that minimum distance is known as Hamming distance. Hamming, we are going to talking about Hamming code. Hamming is the one who has given all this error detection and correction code. So we are going to talk about him when we discuss the Hamming error correction code. But this term is very important, Hamming distance, which is the minimum distance between the code word. And depending on this distance, you can say how many errors can be corrected and how many errors can be detected. And let's see how many errors can be corrected and detected. And that is given by this formula, 2t plus s plus 1 has to be less than equal to d minimum. D minimum is the Hamming distance. So a code provides t error detection, t error correction, plus S error detection only. If and only if this following inequality is satisfied. Okay, let's put some numbers in there. So if we are looking for single error detection, which is also called ACD, that means we are only looking for the S equal to 1 and we are not looking for correction, T equal to 0. So 1 plus 1 has to be less than equal to 2, right? So if D minimum is 2, then we can have only one error detection. Nothing more is possible. And if we are looking for single error correction, no extra detection, that means T equal to 1, S equal to 0. So D minimum between the pair of code words has to be 3. Similarly, single error correction and double error detection, that means S equal to 1, T equal to 1, T is 1 extra error detection, then D minimum has to be 4. So this Hamming distance is very important to know what is the Hamming distance in a set of code word, and accordingly the code will have error detection and error correction capability. That formula that we have seen in my previous slide, 2t plus s plus 1 less than equal to d minimum, can be depicted better pictorially. Suppose this circle is a valid code word and this is a valid code word. And just by altering one, you are getting a error word. So if that error happens, you know that error is there, but you do not know which way to correct it, to make this one to left code word or to the right code word. So if d minimum equal to 2, you can only do single error detection. No correction is possible. Now, if D minimum is 3, you will see valid code word. You change 1 bit, you reach here. You change 2 bits, you reach here. Then you change 3 bits, you reach to another valid code word. So in this situation, single error correction is possible. Suppose this is the error word. So you know that close valid code word is this. So you will be coming here, assuming that one error has happened. Similarly, if the error word is here, then you will be coming back to this valid code word. Or double error detection is possible. Either this you are checking, you are detecting error, or if it is changed to this, you are detecting error. Similarly, here where d minimum is 4, single error correction and double error detection is possible, or triple error detection is possible. And when d minimum equal to 5, double error correction possible, or single error correction and double error detection is possible. Let's see our first error detection code, which is called vertical redundancy check or VRC. It is based on simple parity appending to the information bit or the data word. So we already know what is the weight of the code, including parity and information bit. In odd parity code, there are odd number of ones, and in even parity code there are even number of ones. So it can be created, VRC can be created either odd or even. In this example, it is shown even parity has been applied. So here you can see 7 bits of data, and 0 parity is getting added to the first data. Then second one is added, and like this. Okay, so sender is creating this code word, and now when the receiver is receiving, so suppose here one in the first code word, one bit has changed to 1. Okay, so this error will be detected easily by the receiver, because receiver is also calculating the even parity, and his calculation, receiver's calculation should have been the 1 parity, but what parity it has received is 0. So it knows that this data is corrupted. But suppose 2 bits have changed in the data, first data, then the parity is not changing, right? So receiver will recalculate parity, and parity is also matching. So receiver has no way of knowing that the data has changed and 2 bits have altered. So VRC is a very simple coding. 1 bit is added. It can check only single bit, or it can check odd number of errors, but it won't be able to check even number of errors. Let's see the second error detection code, which is called longitudinal redundancy check or LRC. In this, a block of data words will be arranged in the form of rows in a table, and then same bit position from different data words will be given a even parity. Like here I have 4 data words are there, and here I am calculating the parity bits for this column. So 1 1 0 parity, then here second column has 3 ones, parity is becoming 1, and like this. So here you can see that I am using more number of parity bits. In the VRC, for 4 data words there will be 4 parity bits, but here you can see depending on the data length, which is here 7, I am using 7 parity bits in longitudinal redundancy check. So this will be also sent along with the 4 data words in a block. Now when receiver will receive the data, it is receiving data, it is receiving the sender computed LRC, and when the receiver is recomputing, if 1 bit is error it will find, but here 2 bits of error I will check. No, in the same data what 2 bits have altered, the second bit and the fourth bit. Here you see, here it was 1, here it was 0. So recomputed LRC will be different than the received LRC. So the receiver knows that error has happened. The third error detection code is called checksum. In this, a number of data words are added. Like here, I am showing those data words in decimal number for better understanding the whole procedure. So the first data word was 1, right? In binary, if I say it will be 0101, and 11 will be 1011, like that, but I have written in decimal. So 4 data words, is a block of data words, and that are getting added. A sum is generated, which is becoming 28. Now you know 28 cannot be represented in 4 bits, so this fifth bit is a carry. So that carry is again added to the sum, and now it is called the wrapped sum. And the wrapped sum is coming out to be 30. And then in the third step, the ones complement of that wrapped sum is taken, and that is called the checksum. Now, along with 4 data words, this checksum is getting transmitted. When the receiver will receive these 4 data words and the checksum, receiver will also add all of them, even the checksum. So receiver is adding 4 data words, 1 checksum. It got the sum 30. 30, this one was the carry, so it is also generating a wrapped sum, and that one's complement of the wrapped sum is generated, which is coming out to be 0000. So here the receiver is getting a checksum 0, and if the checksum is 0, receiver knows the data transmitted was good, no error happened. And if the checksum was not 0, receiver will know that error has taken place in the transmitted data, and receiver will discard the data. So in checksum error detection code, the sender side steps are, it is a block coding technique. So in the first step, it will divide the message into 16 bits data word. In the example, I have mentioned 4 bits for easy understanding, but actually the data words are bigger than that, either 16 bits or 32 bits, etc. So it is dividing the data into 16 bits data word. Then in the second step, it is summing all the data words. In the third step, it is adding the carry to the sum and creating a wrapped sum. And then the ones complement of the wrapped sum is called the checksum, that is step number 4. And then sender is sending all the data words plus checksum to the sender. Okay, just like what it is shown here. And in the receiver side steps are, it is again doing all the sums along with the checksum, and then it is also creating a wrapped sum just like the sender did, and then it is also taking one's complement and checking whether the checksum is 0 or not. If the checksum is 0, receiver accepts the data, otherwise it will reject it. Now our fourth error detection code is called cyclic redundancy code. This is also a powerful error detection code used in Ethernet 802.11 ADSL cable. These are all computer networks protocol, and cyclic codes are called cyclic because if a code is cyclically rotated, it will get another code word. Like I will give example of the second code word here. Here 4 bits data word, right? With 4 bits there are 16 different data words, and all of them are getting some redundant bits added. I'm going to talk about how those redundant bits are added. But before that, I'll tell you why this is called cyclic. So I'm talking about this second code word 0001011. Now, if you rotate it, then you are getting this code word for number 8. So from here to here you will get. Like that you can check that if you are rotate a code, you will get another code word. That's why it is called cyclic code word. And now data word is 4 bits long, 3 redundant bits are added. So total code word is 7. With 7 you can have 2 to the power 7. That means 128 code words, but all of them are not valid. Only 16 of them are valid. Now let's see how those redundant bits are added. So there is a key is needed for this code generation, and the key is also called the generator polynomial, and which is also called the divisor. Okay, so a 4 bits divisor has been taken, and then the data words, this is the data word, 4 bits data word, and because the divisor is 4 bits long, 4 minus 1, 3 redundant bits will be added with the data word. And so these zeros, 3 zeros are just the placeholder in the beginning. So this data word and these 3 zeros together will be divided by these 4 bits of divisor, and the remainder after the division is complete, 3 remainder bits will replace this 3 zeros placeholder. So code word will be generated, and that will be transmitted with the noisy transmission line, and in the receiver side it is getting the uh, code word, and this code word will again be divided with the same divisor. So the device sender and receiver both agree on a divisor or a key or a generator polynomial. They both know what is the divisor, and if it is getting a remainder, that is what is called a syndrome. And if the syndrome is all zeros, then it will accept it. And if the syndrome or the remainder at the receiver side is not zero, then it will discard it. So the whole procedure I will explain. So suppose I have a data 1100, and my divisor, which is also called the key or the generator polynomial, which is 1001. And my data is also 4 bits long, 1100, and because divisor is 4 bits, I am adding 3 bits with this number, okay, which I will divide. So now the total thing is 7 bits long, and I am dividing this. And when dividing, it is just we do subtraction, no? Right now, this subtraction is just a XORing. We are going to do XOR. This is called modulo 2 arithmetic. So we do XOR. So here after first we put it here, we do XOR. So I'm getting 101. I need 4 bits, so I'm bringing this 0 down here, and then again dividing. The quotient is not important, so I'm not writing the quotient. And every time I'm XORing, and the beginning has to start with a 1. So with the 0 0 leading zeros, I'm not writing. And then you see at the end of the division, the remainder is 101. And this 101 becomes, instead of 3 zeros, I will replace them with 101. So the code word that will be sent is the data word 1100 and then 101. So what the receiver doing, receiver got this code word, and receiver knows what is the divisor or what is the key, and it is dividing it again. It got all zeros this time, and data is accepted. So this is the procedure. Sender will extend the k data bits with r zeros, and r is the number of bits in the divisor minus 1, and divide by the generator polynomial, that is the divisor, and keep remainder, ignore quotient, replace r check bits by remainder. And receiver side will do one thing, divide and check for 0 remainder. So that is the procedure for cyclic redundancy check. So here you can see when the data, that was the code word generated in the sender side, but data when got transmitted got corrupted. The fourth bit here was 0, here it became 1. So when the receiver is dividing this code word, it is getting a remainder 0 1. And in this case, because the remainder is not 0, receiver knows that data is corrupt, and this data will not be accepted. So this is the procedure. Now the question is how to select the divisor or the key or the generator polynomial. That depends on the data length. Data length will determine how big the polynomial will be, or it also depends on the Hamming distance. Look for a polynomial with a high Hamming distance to maximize the probability of detecting errors. Or choose a primitive polynomial for the best error detection. Choose a polynomial that is considered primitive. And then standardized options are also there. Some well-established CRC polynomials are there, like CRC8, CRC16, CRC32, etc. And they have already proven to be effective. Like CRC8 polynomial will be x to the power 8 plus x square plus x1 plus 1, which is actually 1, 0, 0, 0, 0, 0, 1, 1, 1, right? So this is the ninth bit, because power 8, 0 to 8, 9 bit. So x8 is there, so there is a 1 here. Then the next power is 2, so this one is 2. The next is 1 and this one. Similarly, for CRC16, if this is the polynomial x16 plus x square plus 1, this is actually this big number with 17 bits. So today you have learned about 4 error detection code, and in my next lecture I will tell you what is Hamming code, Hamming error correction code. Hello learners, welcome to my channel RG Global Academy. In this lecture you are going to learn about Hamming error correction codes. I will start with the terminology of this field, like parity check, Hamming distance, and then I will walk you through the steps of encoding and decoding that are required for 7.4 Hamming single error correction code, and then 12.8 Hamming single error correction code. Let's start. Hamming code was invented by Dr. Richard Hamming in 1950. When he was working in Bell Labs, he faced the problem that data is getting corrupted and there was no way of correcting it. Before him, there was ways to detect it, but no correction was still there. So he invented this Hamming code, which can detect and correct both. Dr. Richard Hamming was an American mathematician, and his contribution is immense in computer engineering and telecommunication. He developed L2 programming language that was very prevalent during his time. Later on, Fortran language was developed. He also developed this 7.4 Hamming code, which we are going to learn in detail, and the terminology like Hamming distance, which tells what is the capability of a code word, how many error it can detect and how many error it can correct, etc. So for his contribution, he was also given Turing Award, ACM Award, among many others. So let me tell you first what is the requirement, why it is so important that error is detected and corrected. So in this picture, you are seeing two people, Alice and Bob. They are communicating over the computer network. We call it a transmission line, and they are sending a sequence of zeros and ones, because message or information or data, which is a string of binary bits. One represent high voltage and zero represent a low voltage. So there may be chance that one of the bits get flipped, high voltage becomes low voltage or low becomes high. So during this condition, the entire bit string is wrong. So it is very important that this error is detected and corrected also. Not only unintentional corruption of data, sometimes intentional corruption of data also happens. As seen here, Mallory is the guy who is including their communication between Alice and Bob. Maybe he is the one who is changing these bits. So for any reason, intentional or unintentional, if data is corrupted, that needs to be detected and corrected. That's why this field is so important, And fortunately, Richard Hamming invented a code which can detect and correct errors, and we are going to learn about it now. Data can be corrupted during transmission, but not only during transmission, it can be corrupted when data is stored in memory inside the same computer. So the solution is to detect the error and correct it so that you get the right result. And before going through that procedure, let's see some definition about types of error. Uh, the data can be corrupt in a single bit position, which is called single bit error, where it is shown that sender is sending these 8 bits of data and receiver is receiving, but in 1 bit position, the 0 flipped to 1. And that is what is called single bit error. This bit flip can happen in multiple bit position also, like it is shown here. Here this 1 became 0, sender sent 0, it became 1 here, 1 here. And there are 4 bits that got flipped, but the span of this error is 8. So it is called burst error, and the burst length is 8. Single bit error is more frequent than burst error, and we are going to see Hamming code which can correct single bit error. To detect and to correct errors, sender sends extra or redundant bits along with data bits, and this mechanism is called encoding. Sender side has one encoder. It will take the message or useful information bits, which is called the data. It will feed it to a generator, and the generator will decide how many extra redundant bits are required and where should be their values. And it is generating data and redundant bits together. These redundant bits are also called check bits. So data and check bits together, it is called code word, and this encoder is generating the code word at the sender side, and then the code word is sent through the noisy transmission line, and after receiving the code word, receiver will send it to a checker to check whether the code word that he has received is right or wrong. If right, then it will extract the data, and if wrong, if the checker has the capability, or basically if the code word has the capability to correct itself, then the checker will correct it and send the right data. So as I said, 7.4 Hamming code can detect and correct single error, and even we are going to see a bigger example of 12.8 single error correction code. So at the receiver side itself, the code will be corrected. If the correction capability will not be there, then the receiver had to request the sender to retransmit the data. But at the receiver side, if this correction capability is there, then it is much more efficient, because again you are retransmitting the same message with noisy transmission line, so that efficiency is not that much. So correction capability at the receiver side makes the communication much more efficient. Here I will show you some example of data words and code words. In a block of data, this block of data is divided into data words, each k bits long. So with k bits, there can be 2 to the power k data words, and r extra bits are added with k bits. So the length of the code word will be k plus r, which we can call it as n bits. So with n bits, there can be 2 to the power n code words, but not all code words are used. Only 2 to the power k code words are valid and others are not used. Why? Because if the code words are very close to each other, then it is very difficult to correct the code. Like here I am showing a table of data word and code word. Data word is 4 bits long. So with 4 bits there can be 2 to the power 4, 16 valid data words are there. And now you can see with every 4 bits, 3 redundant bits are added. And now the whole thing together is called a code word. And the way the code words are assigned 000 here, then the next one 011, that technique we are going to see. But you can see that if the code words are uh, vary from each other, maximum distance is there, then it is better for the detection and correction capability. So how the I will tell you the mechanism by which the distance between code words are found. So each code word is a string of zeros and ones. Depending on number of ones in a code word, it is called the weight of the code word. So if you take example of these two code word, so this code word has 1, 2, 3 ones, and the next one has also 3 ones. So their weights are same, but you can see in how many bit position they are different. They are different in this position from most significant bit. This is the third one, then fourth one, then the fifth one, and this one. So there is a distance of 4. In 4 bits position, these two code words are different, and that is what is called Hamming distance. But this distance is not constant. If I see two other code words, this code word here and this code word here, and same way you see in how many bit position these two code words are different, you will see the distance between these two code words only 3. And 3 is the minimum distance between code words. Like that you can check the distance between all pair of code words. And the minimum Hamming distance tells what is the capability of these code words. That means how many error it can detect and how many error it can correct. So this minimum Hamming distance is very important. The next slide is also telling what I just said in the previous slide. What is the weight of a code word? That is the number of ones in code word I. And distance between code word I and J is the number of bit position in which I and J are different. So if I is this code word, J is this code word, their weight is 4 and 3 respectively, and their distance is 3. And Hamming distance is the minimum distance. Maybe there is more distance between code words, but we will go with the minimum distance between any pair of code word, and that determines the capability of that set of code words. How many errors it can detect and how many errors it can correct. And that is given by a formula which is given here. 2t plus s plus 1 has to be less than equal to d minimum. D minimum is the Hamming distance, and t is the number of errors it can correct, and s is the extra error that can be detected, and this one is a constant. Now if we put numbers in there, then we can see if s equal to 1 and t equal to 0, then d minimum required is only 2. With minimum Hamming distance of 2, only single error detection is possible, no correction is possible. But if d minimum equal to 3, we can make t to 1 and s 0, and then we can have single error correction or ACC. So this formula is very important, that tells how many error can be detected and how many errors can be corrected, and this d minimum is called the Hamming distance, which is the minimum distance between the code words. And if the Hamming distance is 4, then one error correction is possible, or double error detection is possible. One ACC plus, see, we'll put t equal to 1. So here we are getting 1, and here we are getting another 1. So correction means detection first, then correction. There is one detection and here is another detection. So 2 error detection plus 1 error correction is possible if d minimum is 4. Importance of the Hamming distance can be understood better if the problem is depicted pictorially. Like here, you can see that these circles are representing code words, valid code words, and when some error is taking place, it is changing that code word. Suppose it is here. Now, if that error word is equal distance from two code words, then you don't know in which way is the correct one, right? Correct code. So there only detection is possible, correction is not possible. With the d minimum 2, because from here you are going to error word, and from error word you can get to here. So d minimum is 2 between the two valid code words. So if the error is here, which is equal distance from two code words, it's not possible to correct the error, because it can be this code word may have changed or this one, but you can detect that there is an error. And if the d minimum is 3, suppose this left hand side code word one bit got flipped and the error word is this one, then assuming that there is a single bit error has happened, it will come back to this valid code word and not to that one. Okay, so that's why it is called single error correction. And in any place the code word is, it can be detected, so it is called double error detection or single error correction. And if d minimum is 4, then if the code word is here, error word is here, correct one will be here. It is a single error correction, right? But if the error word is here, then it cannot be corrected because it is equal distance from two valid code word. And you can reach here only when two bits are flipped, right? One bit flips, it will go there. Two bits flip, it will go there. But if that is the case, correction is not possible, but it can detect the error. And then likewise for the minimum 5, it is double error correction is possible. If one error happens, this code word is closer, so this is the right one. If 2 bits error happens, still this one is the closer, so this is the right code word. And single error correction and triple error detection is possible like this. Now let's see the 7/4 Hamming code, which is a single error correction code or ACC, and it is depicted pictorially again. And 7/4 means length of the code is 7 and 4 is the length of data. So 3 redundant bits are used, and here 4 data bits are already shown, and it is a Venn diagram, and 4 data bits are placed here, and in every circle you will be placing a parity bit, and you can see 3 parity bits will be placed, and each parity bit is covering a subset of the information bits. So here in this circle, if you put a parity, it will be covering this data bit, this data bit, this. 3 data bits out of 4, 3 data bits will be covered by parity 1. Similarly for parity 2, these 3 data bits will be covered. If I call the data bits D1, D2, D3 and D4, then here it is written P1 is covering D1, D2 and D4, and this is a parity checking, even parity. If we say, it will count the number of ones already there in the data, and to make it even, it will put a 1 here, and if these 3 already even, then the parity will be 0. So let's see here, the sender is doing all this encoding, right? Sender knows this is the 4 data bits, and suppose this parity needs to be calculated. 3 ones are here, which is odd number, so the parity bit value P1 will be 1 here. And for parity 2, because the 2 ones are here, to make it even, it will be 0. And for this also, 2 ones are here, and this parity will be 0. And it is telling which parity is covering which data bit. Out of 4, 3 are covered. So multiple check bits are employed in 7/4 Hamming code. 3 check bits. Each check bit covers a subset of the information bit, and subset overlaps so that each information bit is at least in 2 subset. So after putting the parity bit, sender is sending it, right? Or maybe this data is saved in the memory as a code word and something happens and data is getting flipped. It was 1 before and this is 0. So if it is sent through the noisy transmission line and this bit got flipped and it became 0, now the receiver will calculate the parity again. So when it is checking the parity and he knows that it is a even parity system, if it is 0, 1, 1, then it shouldn't be this parity that he has received, should be 0 and not 1. Okay, so he knows there is some problem in this circle. But in this circle, 3 data bits are there. He has to pinpoint. First of all, he detected it. Now he has to pinpoint which 3 is problem. Now this parity will also be also getting recalculated, and here there is a 0. If this parity 0 1 0, then there should be an 1, right? So it is the problem between this parity bit and this parity bit, and this parity is okay. These two ones are there, parity is 0, it is okay. So problem is in red circle and blue circle, and red and blue common is only this bit. Other bits are this bit is also common, but this bit is for the green circle also. Only the bit that is common in these two circles. That means the parity that is covering this bit, uh, that is the problem bit, and that will be flipped. That 0 will be flipped to 1, and to make all the parities even parity. And this is the way 7/4 Hamming code can do single error correction. So to achieve the same thing more systematically, the data bits are represented as vector of length 4 because our data word is 4 bits long. So data bit 1 is 1 in one position and other are 0. Similarly for D2 it is set to 1 and in other position set to 0. So these are the 4 data bits, D1, D2, D3, D4. Similarly for parity bits, depending on which data bits they are covering, they are set. Like parity 1 is covering D1, D2 and D4. Parity 2 is covering D1, D3, D4. Parity 3 is covering D2, D3, D4. And when you write parity bits and data bits all together, it will be a 4/7 matrix and it is called a code generator matrix. I have depicted the parity columns blue and data columns with black color, and the data columns are a identity matrix. They are say in the diagonal position it is 1, and then the actual data to generate the code, suppose the data is 1011, so this 1011 will be multiplied with this code generator matrix and it will generate the code, 7 bits long code, and out of that this 3 bit is redundant bits or parity bits, and last 4 is the data bit. See the last 4, the data here 1011. So 1011 and 010 is they are 3 parity bits. That is the way it is mathematically computed. There is another way to compute. I will show that also to you. Now let's see what the receiver will do after receiving the code word. It will check whether the code word received is right or wrong. It will look for error, and if error is found, it will correct it. So if the receiver received this code word 0101010, in the previous when the code was getting computed by the sender, it was 1011 here, right? So one bit has flipped and it became 1010. So receiver knows first 3 bits parity and last 4 bits data. So it can also calculate the code word taking that data 1010 with the code generator matrix. It is getting a code, and here it is getting a parity bits which is different, 101. It received 010 with the same data. It is generating different parity bits. So the receiver knows that there is some problem. So it takes out the received parity and recomputed parity, and if they are XORed, it is generating 111, and it is called syndrome word. If the syndrome word is not 0, that means error has happened. If the syndrome word is 000, no error has happened. Now, after knowing the error has happened, this syndrome word 111, which is 7, right? So this says the 7th bit position has flipped. You know that everything we are numbering from here 1, 2, 3, 4, 5, 6, 7. So it knows that this bit position has flipped, and it will make the correction with 1011. Okay. Either it is done this way, or there is a checker matrix is also there. It's a 3 by 7 checker matrix called H. First 3 column is for the parity bits identity matrix. Only one is there, diagonally ones are there. And then last 4 columns are for the data bits that each parity is covering. Like parity 1 is covering data 1, data 2, data 4, parity 2 covering data 1, 3 and 4. Parity bit 3 is covering data 2, data 3, data 4 bits. So this checker matrix will be multiplied by the received code 3 by 7 matrix, 7 by 1 matrix, and it will get a vector 3 by 1 syndrome word vector. And if the syndrome words are not all zeros, error has happened. And this 111 is saying it is a 7th bit position where the error has happened. So it is corrected in this way. Now we are going to see a bigger problem. But before that, let's go through the error correction steps again. When data is saved in memory, M is the message bits, M number of message bit. And previously we were depicting with data bits, right? You can call it as message bit also. And K is the code bits. Codes have been determined by the generator in the encoder side, and it is saving M plus K bits here. And when data is getting retrieved from memory, message is getting retrieved and the parity bits are getting retrieved, then the parity bits are again recomputed, which is coming out to be K prime, and they are compared because now it is going to give the syndrome word. If both are same, syndrome will be all zeros, and if not, the syndrome word will tell how to correct it and data will go out. Okay. And if the parity bits have no data correction capability, then it will give a signal that error has happened. Now see if the data size is bigger. Previously we gave example with 4 bits data, 3 bits parity is required. So there is another formula by which one can determine how many parity bits are required. And that is given by this formula. 2 to the power k minus 1 has to be greater than equal to m plus k. M is the message bits, k is the parity bits or redundant bits, and this k is here. 2 to the power k minus 1 has to be greater than equal to m plus k. So if my data bits is 8, then the check bits required should be 4, because 2 to the power 4 minus 1 is 15, and 15 is greater than 8 plus 4, 12. If you take 3, you cannot satisfy this equation. 2 to the power 3 is 8 minus 1, 7, and 7 is not greater than 8 plus 3. Okay, so like that way, if the data bits are bigger and bigger, number of check bits required is given here, calculated according to this formula. And also it depends on the aim of the correction is single error correction, and if the aim of the correction is ACC or double error detection, then the check bits are getting one more. Every time it is one more. And then the percentage overhead is also given. If data bits 4 bits, check bits 4, then 50% overhead. But as the data bit size is increasing, then the percentage overhead of the code word is decreasing. Now let's solve a bigger problem where the data bits 8 bits data, and we already have seen from that table that 4 redundant bits are required. So total code word length will be 12. So we can call it as a 12 by 8 having single error correction code. And this time, instead of those generator matrix and checker matrix, we are going to solve it in this tabular fashion, because we also have to know no which code bit or the parity bit or the check bit is covering which data bit. So here we are creating a position table with the first row is position number of the bits, position 1 to position 12, because there will be code word length is 12, and these positions we have written once with the decimal number, and next row we have written the same thing as a binary number, because we need this binary position number. We are placing the check bit where the position where there is only one. So check bit 1 is in position 1 and check bit 2 is in position column number 2, and then check bit 3 is in column 4, because in third column there are two ones in the position number where we cannot place it. Similarly, for check bit 4 we are putting it in position number 8, because there is only one in this position number. And this time just keep a note that we are counting the position number from the right hand side. Previously, we counted the positions from the left-hand side. So it will be just a mirror image, but the way you are putting it, you keep a note of that. So the first column is check bit 1, column 2 check bit 2, column 3 check bit 4, check bit 3, and column 8 check bit 4. And in the rest of the position number, you place the data D1, D2, D3, D4, D5, D6, D7, D8. And now these positions are telling that this check bit 1 will cover which data bit. Check bit 1 has a 1 in the first one, no? So it will cover the data uh, in the position number where there is a 1 in this place. Here there is a 1, here there is a 1, here there is a 1. This one doesn't have a 1 in the first place. 2 to the power 0 is not there. So, and then next one is this one, and next one is this one. So C1 will be covering D1, D2, D4, D5, and D7. And it is a even parity checking. So it is going to check D1 XOR D2 XOR D4 XOR D5 XOR D7. Is it understood? Now let's see what check bit 2 will do. This is check bit 2, which has a 1 in the second position, and it will be covering the data which has a 1 in a second position. So it is covering D1, then D3, then D4, D6, and D7. Okay, so it is written C2 equal to D1 XOR D3 XOR D4 XOR D6 XOR D7. Now check for check bit 3. Check bit 3 is here, the arrow is put here. And it will be covering D2 because check bit 3 has a 1 here. And D2 also has a 1 here. Then D4 has a 1 here. Next should be D7 and D8. Okay. So check bit 3 is covering D3, D4, and D8. So D2, D3, D4, D8. D2, D3, D4, and D8. Okay. And the last one is C4. C4 is this check bit 4, and it is going to cover rest of the data bits because C4 has a 1 here, and this position also has a 1 here, 1 here, 1 here, and 1 here. And in this position, D5, D6, D7, and D8 is here. So C4 is D5 XOR D6 XOR D7 XOR D8. Okay, and this is the way the code words will be generated. After you know the check words, you can just put all the data bits together and all code bits or check bits together. You do not have to interleave them like this. So now we are going to generate the code word. 12-8 code word we are going to generate for data word 00111001. 8 bits long data word. You have created the table, you have put noted their position, and you put the check bit in their proper column. You have put the data bits in their position, and you already know which check bit is going to cover which subset of data bits. Okay, now you are going to generate the code word. So let's put the data. Data was 00111001. Same thing you put it here also. So C1 will be this. You will be XORing this 1, 2, 3, 4, 5 bits, and you have to make it a even parity. So check bit 1 will be 1. Similarly for check bit 2, there are 3 ones. So check bit 2 is also 1. Check bit 3, there is only 1. So here also it is 1. And check bit 4, there are 2 ones. So here the check bit is 0. So the code word will be, now you are just putting all code words together. First 8 bits for data bits and the last 4 bits for code bits. So code bits are 0, 1, 1, 1. This one is C4, C3, C2, C1. And the data is D1, D2, D3, D4, D5, D6, D7, D8. Okay, so you remember the code word, and suppose the data gets corrupted. Now we are going to see how the receiver will correct it. So now it is saying, suppose the code word has changed from this one to this one. Where is the change? This position. D3 position has changed. Okay, D3 was 0 before, and now D3 has become 1. 1 bit error we are going for. So we already know the table where to put the data, where to put the check bits, and which check bit covers what. So at this time, the receiver will recompute the check bits. It already knows these 8 data bits, and it is recomputing the code word again. So C1 came out to be 1, C2 came out to be 0. So it is not matching. C3 came out to be 0 and C4 came out to be 0. So it is not matching, right? Here it received 0, 1, 1, 1, and here it generated 0, 0, 0, 1. So now it is going to uh, calculate the syndrome word. It will just XOR the recomputed code with the received code, and that will give the syndrome word. And the syndrome word is coming out to be 6. So it knows that 6th position the error happened, and in the 6th position D3 is there. So it has correctly identified that this bit has flipped, and it will put it back to 0. This is the way it is done. So error occurred in 6th position where D3 is there, and it is now corrected. Okay, learners, previously I created 2 other videos about error detection, and I also created computer codes like ASCII, Unicode, BCD, Huffman encoding lecture video. If you want to go through them, the links are given here. And thank you for watching this lecture video. I'll meet you in my next lecture video again. Thank you.